Hi, I'm Steve Ward, and in this session we're going to talk about computer technology, particularly as it relates to industrial PCs and for use in embedded applications. Now, just be aware, this is a tough session for me to present because computer technology changes so fast. Typically, there will be new computer architectures every few months or years. There's new CPUs every few months or years as well. Industrial PCs and embedded applications tend to lag behind that a little bit, but even so, what's in this slide deck may be out of date by the time you get round to actually viewing this video, but it will give you a good indication and you'll be able to go and research additional information to bring yourself up to date based on what I'm going to talk about. Let's start by defining what is an IPC and what is embedded computing. So from Wikipedia, an embedded system is a computer system with a dedicated function within a larger mechanical or electrical system, often with real-time computing constraints. So consider, for example, an industrial application, or maybe an infrastructure application, a locomotive, for example, or a train engine that uses a computer for real-time purposes. That would be an example of embedded system. Perhaps a power station where you've got a gas turbine and the gas turbine is being controlled by industrial PCs or industrial computers. So that could also be an example of an embedded system. So one way to describe this is to say that industrial computers or IPCs are embedded, i.e. they're inside a larger machine, and it's the machine that's the application, and it's that IPC or embedded device that helps make it run. Sometimes the embedded computer could be a PLC, a programmable logic controller, so that's a specific category of industrial PC, and I won't refer to that too much, although today if you do look at a PLC you'll see that some of the architectures are similar to industrial computers. But more likely an industrial computer will be used for something like data collection, possibly for local HMI SCADA, maybe for doing some higher level control above the PLC, such as an advanced algorithm for optimization of control. But ultimately, it's all part of the larger machine application. Now, the key point is industrial PCs aren't like commercial desktops or even servers. They're similar, but one of the key differences, they use industrialized or ruggedized version of components. So they're intended to run at higher and lower temperatures. They're intended to be more proof against shock and vibration, and there may be other aspects as well around the physical hardware that makes them a bit different. Even as simple as using industrialized connectors, which have screws to stop cables falling out. Now, because we have a real-time computing system, there are constraints that mean there must be a guaranteed response time to a system event. But we can be flexible here. Guaranteed response time doesn't necessarily mean it has to happen at a particular time. It might just mean that it has to happen within a maximum time, but a shorter time would be acceptable. But as long as it doesn't exceed the maximum time, that's also acceptable. So real time can mean different things to different people. And it depends on the speed of the system as well. Some people think real time means responding down to a millisecond level, which is one consideration or one possibility. But equally, a real-time system might just be that it has to operate within the constraints of the machine. So if you've got a machine that has some sort of operational time within a few seconds, real time might be as long as that few seconds response time for the machine to operate. But usually when we talk about real time, we do mean fast response. Certainly not minutes, sometimes not even seconds, ideally fractions of a second or even milliseconds. Now, another aspect of the industrial P, as well as performance and the type of components we use, we also find that OEMs are often validating their systems. So they will buy the hardware, they will configure the software, and then they will provide that as a solution which is guaranteed to work. And that solution needs to be provided for quite some time. Could be 5 years, could be up to 10 years. And the reason for this is, first of all, the machines that these are going onto have a long life. We're not talking about like a laptop, which is replaced every 3 or 4 years. We might be talking about a large machine, like a gas turbine. The operational period for a gas turbine could be decades, 30 years, maybe longer. So the OEMs have to be able to provide this long-term supply of the same configuration that both avoids regular revalidation against new configurations, but it also means that the user of the machine doesn't have to continually update their system, and they can continue to have multiple systems which have the same sets of hardware. That reduces things like spares holding, it simplifies maintenance and configuration activities, and there's a lot of activities around that and a lot of other things around that which mean that this long-term supply is very important, which is certainly not the same as the commercial PC industry. Now the IPC market is typically split into two, and the market share is about even, but some people have different ideas of what an industrial PC market or an industrial PC even might look like. So for me, the way I see it is the first half of the market is the IPC only. So this is the computer core, it's just the box that has the computer, the CPU, the memory and so on. And this is typically a headless or standalone box that doesn't have a display connected. So these sorts of devices are used for data collection, they might be used for local analytics, they might be used for edge aspects, they might be used for even real-time control, and they could be a server for HMI SCADA application. Edge could include all of these aspects, including local data storage, gateways, and anything from simple to very advanced analytics. Now with an IPC, typically it's the raw processing performance that's of most importance. Because there's no display connected, you're not really worried about graphics performance. Instead, you want a powerful box, but the box will just be sitting there acting as a server to other applications and possibly controlling I/O and performing communications. But there's no user using the system. There's no keyboard, no mouse, no display. Now the other half of the market is displays or panel PCs, and this is an industrial PC that's combined with a screen. So often it's a single device, you'll have a display, and then mounted on the back of that display is the industrial PC with all of its ports and connections and so on. These are normally used for HMI SCADA, and they can either be the server and the client in a single box, so we're at sort of like an operator interface level or a machine control level. Sometimes the HMI SCADA might be in a different box. There might be a separate server running in an industrial PC, or maybe even the HMI SCADA is running on a separate rack mount computer or even a desktop computer sometimes, or a workstation class computer, in which case the panel PC is just acting as a client. So there are also some client-only applications which are outside the scope of HMI SCADA. For example, kiosks, where you're maybe just serving up a web page from a remote server. Also, that could include remote desktop protocol, RDP, or terminal services, or whatever technology Microsoft or other people call it these days. Now, usually with a panel PC, because most of the operations are user-driven, graphics performance and user response is usually of more importance than the raw processing performance of the CPU itself. But there is an overlap between these two. If you're using a panel PC as a HMI SCADA server, then you may also be running local data storage, you may be using it as a gateway, you might even be running analytics on there, in which case you might have a blend of the two where you need both raw processing performance and you need the graphics performance. So there's a wide range of panel PCs going all the way from very simple low-cost devices with limited performance all the way up to quite powerful devices which include that display. Another possibility, of course, is you could use an industrial PC with an industrial monitor. So then you have your high performance industrial PC, and then you'd use a HDMI or DisplayPort cable, and that would connect to an industrial monitor, and you could then have the benefits of both of these with an IPC and a display. So the market is quite mixed, but depending on who you're talking to, of course, you'll need to understand what their requirements are, and based on, is it more visualization, is it more processing, is it a combination of the two, then you'll be able to understand what the requirements are and what the best solution is. So as I mentioned, a common variation is the industrial display, which is a screen only, which you can connect via a cable to an industrial PC. Or possibly you might even use a commercial PC. I've seen users do this before. They buy a standard commercial PC to go inside their panel, but they need something industrialized for the operator to interact with. So in this case, you have an industrial display, no real intelligence there, but it connects to your computer, whatever your computer is, industrial or commercial, again via this HDMI or DisplayPort cable. You may also need another cable for a touchscreen. So often with these industrial displays, or also industrial monitors as they might be known, they often have a touchscreen. So you'd need both the HDMI or DisplayPort cable, and you'd also need that additional USB cable for the touchscreen. Sometimes the industrial display might not have any touch capability. It's also possible to have a separate user interface, such as an industrialized keyboard, or maybe an industrialized trackpad, or some other device. But you need to consider that input, but that may be combined with the industrial display, or it might be separate. There's also a category of what we call a web HMI. Web HMI is a low-powered computer device, typically using a very simple CPU, and that just runs a web browser. So the idea of a web HMI, this is often combined with a central server, and then you could run that web HMI as like a kiosk type device, or possibly you could be using some sort of web-based graphics, possibly extending to a thin client, maybe using RDP or so on. But normally these web HMIs are very low powered computers. That brings the price down, but it also brings the performance down considerably as well. But in this case, typically the web HMI is a web browser only, and it would have to connect to some sort of server device. Now, IPCs may have some specific requirements depending on what the user requires. They may need industrial mounting, so that could be panel mounting. Panel mounting is good because panel mounting is normally the most secure against shock and vibration. And also, if you've got a good physical connection to the panel can form part of your heat dissipation, so that can help your industrial PC run at a lower temperature compared to, say, a DIN rail. So with a DIN rail is more convenient because you just put a DIN rail on your panel and then you just clip the industrial PC onto the DIN rail, but it's not so secure against shock and vibration, and you don't get that temperature or heat transfer, so not so useful for dissipating the heat, but much easier in terms of installation capability. Now, occasionally you do see industrial PCs that are rack mounted, but if you look at a traditional 19-inch rack, that's more associated with a commercial server. An industrial PC normally wouldn't be rack mounted, although there are some industrial computers that are rack mounted. Now, you may get a modular enclosure. Modular enclosure can give you the benefits that you can expand the computer when it's installed. So for example, you might have a modular enclosure for the extra connections on a PCIe backplane. So you might have a industrial PC that's slimline with no connections, or there may be a modular enclosures which allow it to be expanded to have 1, 2, 3, 4, or however many PCIe slots you need. So modular enclosures, that's normally something the vendor would prefer because it reduces the number of models the vendor needs to make, but it can also help upgradability in the field if anything needs to be added or modified in the future. Now, IPCs typically have a large number of connections, including legacy ports. I've got a laptop on my desk in front of me. It's just got 2 ports. It's got 2 USB-C ports, and that's it. One of the USB-C ports is power, and the other one is used for whatever else you want to connect to, and that's it. The majority of the connections on a modern laptop are wireless and Bluetooth and so on. An industrial PC normally needs actual physical connections, and often quite a few of them. So an industrial PC may have multiple Ethernet connections. It may have multiple serial connections, particularly legacy RS-232 and RS-485. It may need additional PCIe interfaces to allow you to connect to other interfaces like Profinet or Profibus or DeviceNet or so on. And it may also need more USB connections to allow you to connect devices. And there may also be a requirement to connect to multiple monitors as well. So you may find there are multiple connections for monitors. So IPCs may have a large number of connections in order to physically connect to all of those devices that are part of the industrial process. IPCs often have enhanced electrical noise immunity or EMC capability. Inside a typical panel, there is some degree of protection from the metal nature of the panel itself, but if inside the panel you're also running high voltage equipment, you may be running variable frequency drives, you may be routing power to motors, via contactors and so on. So there can be quite a large amount of electrical noise even inside what would essentially be a shielded cabinet. So IPCs are often constructed from metal enclosures and they have a higher level of EMC capability. Shock and vibration, we talked about that, but IPCs often need high levels of shock and vibration technology. So vibration is if you've got like continual movement, so maybe there's a large motor nearby and that can lead to vibration. Shock, again, think about that railroad application. If you've got an IPC mounted on, say, a locomotive, when that locomotive is going towards another unit to form a consist, there's a big shock, several Gs, when it actually combines with the other carriages and so on that form that total train. So, potentially large levels of shock, high levels of continuous vibration. Now, heat is an issue for industrial PCs. Again, they're mounted inside a panel. We often want to have low levels of heat, and that typically means low level of power. But low power might also be derived from wanting to run these from, say, a solar panel or a UPS type arrangement. So the lower the power, the better, because the longer the UPS will last, or the lower the solar power needed. Low power is also good because it minimizes the amount of heat dissipation inside the cabinet itself. Lower heat also extends the life cycle of the unit. Units which run at higher heats tend to reduce their life because the heat affects the electronic components and can reduce their life cycle. And low power might also be desirable for something that's on 24/7. Just having low power can also reduce the cost of ownership. You might find that a high-powered industrial PC, the cost of the industrial PC might even be dwarfed by the amount of power it takes over its long life cycle. So low power can help with that total cost of ownership. Long life, typically you're looking at a life cycle from the vendor of 5+ years, possibly as much as 10, maybe even more. I've worked for some power industry customers in the past where they wanted availability of components for up to 40 years. But that was highly specialized. It means manufacturing and sourcing lots of components, keeping them in a nitrogen sort of cooled environment so you can continue to manufacture them. But otherwise, even in a standard environment, the user probably wants to be able to buy these for 5 years plus, partly because of the life of the asset, as we mentioned earlier, but also the cost of validation against any new sorts of operating system or application or whatever else that comes out. There may also need to be specific agency approvals. UL is common for the US, combined with what is now, I think, CUL, which is the Canadian version. In Europe, there's CE mark. There may be other agency approvals that are required, but for use on marine environments, then you may need those specific marine agency approvals as well. So DNVGL, Lloyd's, ABS, and so on. So there may be specific approvals beyond what you'd see in a normal computer. Having said that, industrial PCs do share many components with commercial computers, but as I mentioned, the components may be based on the same raw manufacturing capability, but they may be industrialized in terms of, they support higher and lower temperatures. And then you also have the actual construction mechanism, which can make the computer more industrialized as well. Now, one thing about industrial PCs is generally the focus is on hardware. Many users, OEMs, they often install their own operating system and software stack. Otherwise, you'd be looking at support from Microsoft or possibly Linux distributions. But generally, the IPC itself, the focus is very much on the hardware itself. And the software, yes, of course, you do need software, but often that's not the focus. That might be different in a display product where you might be looking for a particular operating system. Operating system support can be part of your specific requirements. Typically today, we would run Windows 10, even though Windows 10 is coming to the end of its life for desktop applications, Windows 10 is still very common in industrial applications. And what we use for those is we use Windows 10 IoT Enterprise, which is the same as full-blown desktop Windows 10, except for we use the IoT version, which has some of the bloatware removed. So, for example, it doesn't ship with games. Windows Update is optional. And also it has the LTSC version, which means long-term service channel, which gives it extended support beyond the normal desktop versions of Windows. So there may be some aspect to do with software, but typically the focus is on hardware. And that can get very focused, highly focused on the specific construction of the industrial PC. All of the little tweaks that the vendor does to make it proof against shock and vibration, and lots of other techniques that the vendor needs to consider in order to meet the long life cycle and also have a good design that's capable of coping with the industrial environments it's going to be installed in. Let's take a look at some architectures. Now, since I've been involved with computers, architectures have changed quite a bit. Early systems typically used multiple chips mounted on a large motherboard, and the motherboard was called as such because it was the board onto which all the daughter boards were connected, hence daughter board, motherboard, and that's the way that the naming arose. Chips could be soldered, sometimes they were socketed, some components might be mounted via connectors, and there have been a variety of different options over the years. For example, in the past we've seen sockets for CPUs, we've seen dual inline memory modules for RAM interfaces, and then there may be a variety of other connects to other devices using a variety of different interfaces. So for example, PCIe, USB, in the past some of those would have required their own chipset as well. And what you'll also find in these systems is the motherboard often includes the power conditioning circuits. Now, more modern systems have more modern integrated designs, and there is more and more functionality contained inside the CPU, which means the motherboard can get much simpler. If you look at a modern motherboard, there's often very few components, very few connectors, and the reason is that modern CPUs include most of the interfacing functions and of course graphics capabilities, which in the past would have been separated out onto separate boards. One of the reasons for doing this is the CPU vendors themselves, they want to simplify the systems, and they can sell more or have more expensive CPUs by having more functionality. Another reason is that the CPUs themselves, if you've got everything integrated on the same silicon, on the same die or the same chip, that can also make the CPU much faster. So that there's benefits both for the vendors of the CPUs in terms of the costs, but also to the users in terms of the complexity, and everyone benefits from the improved performance that we get. So let's compare some computer architectures. If we start on the left with what would look like a legacy architecture, this is where we had a large old motherboard, and on the motherboard you'd have a socket for the CPU. So you see the CPU at the top there on the left hand side picture. There would be a separate system clock. The clock provides all of the signals that control the CPU and when for it to operate. In these legacy systems there would then be a couple of chips, so you'd have a north bridge which would give you the interfacing to the higher speed devices, and then you'd have a south bridge which would give you an interface to lower speed devices. So higher speed devices could include the memory bus integrating to the random access memory or RAM, and then often there would be a separate graphics bus which would integrate to the graphics processor. Typically in these older legacy architectures, the CPU didn't include any graphics capability, so you did need some sort of separate graphics coprocessor. And then there would be an ISA or a PCI bus connected to the south bridge, which would give you expansion cards. So that would include things like sound cards and other interface cards. In the early days, even an Ethernet interface had to be handled via one of these old legacy expansion cards. The south bridge in later systems would also give you the Ethernet interface itself, but as I mentioned, in the older systems, it was a separate card. USB ports as well. When USB first came out, that would have been a separate PCI or ISA expansion board, but later built into the south bridge. And then the south bridge supported ATA, which is an attachment interface bus, and that was used for legacy hard disks, and later for SSDs, but SSDs came along a lot later. So in the early days, hard disks were rotating platters, typically made out of glass or maybe aluminium, and then on that was a electromagnetic coating, and there would be a head which moved over the hard disk to read and write that electromagnetic coating and to read and write the data. So lots of components, lots of complexity, relatively low performance. And over time, what happened, more recent architectures started to combine some of these capabilities. And one of the ideas was to improve performance, but also, again, it was to reduce the complexity. So what we see in a more recent architecture in the middle here, you'll see the CPU. It would have a direct interface to the memory bus, so the North bridge is effectively now integrated into the CPU, and you've got a direct interface to the memory bus. You'd have a direct interface to the graphics bus, so that would improve your graphics capability, again because you've got direct communications with the CPU. Typically there in these systems, the graphics processor was still a separate board, and the graphics processor would have its own graphics RAM. So the idea there is that because the graphics processor's got its own RAM, it's not sharing system RAM, so that means that your local RAM interface to the graphics processor can be a lot faster. And if you look in a modern gaming computer, you'll probably still see that. You will have a separate graphics processor with its own memory, and that will be separate to the standard memory that's used by the main computer. Now in these old systems you had the CPU, and then there would be a direct memory interface to a peripheral component hub. So effectively the peripheral component hub is combining most of the aspects of the South bridge and possibly some of the aspects of the North bridge. So this would give you a higher speed connection to your hard disks. And then we start talking about M.2, which is a later technology, which gives you a faster interface to faster disks, particularly when we get to SSDs, where you need a much faster interface. There might be direct interfaces to expansion cards, typically using PCIe. So PCIe is a later version of PCI, which gives us faster throughput. And then that PCH, that would include aspects like Ethernet LAN, audio. Some systems still have separate audio chips, but often now audio is all built in, and then USB hub with multiple USB ports. So getting a bit more integrated. And then what we see in the modern current architecture, we see a much more integrated device. So now we have the CPU, we have a GPU, so they're often combined on one chip. So we have the graphics processor as well as the main CPU. The PCH, the peripheral component hub, that's also built in. So effectively now, we've got a much smaller number of chips. And often now it's a single chip. If you open up a modern computer, you'll see one big chip, which is that main CPU, and that includes graphics. With the local graphics, it can share the main memory bus, so we can use a single set of RAM for both graphics as well as for the CPU and everything else it does. There's now an M.2 bus, which gives us high-speed interface to SSDs. Yes, older hard disks are rarely used now. We have the direct interface to expansion cards using whatever interface it is, M.2 or maybe PCIe or others. And then again, you've got Ethernet, you've got audio and USB hubs. But what it means is as you move from left to right, the number of chips on the motherboard dramatically shrinks. And that allows us to have improved performance because things are more integrated, but it also allows us to have smaller devices. So again, if you look in, say, a modern laptop or a modern industrial computer, you'll see the architecture looks a lot more like you have on the right. And if you go up to a desktop computer, you still see that current architecture on the right, but now you may also have a graphics processor. That's often what you will see in a higher performance gaming computer as well. You will see that architecture there with combination of everything, and then you'll have a separate graphics processor because that's always going to give you faster graphics performance. And that graphics processor has its own RAM as well, again, for increased performance. One thing I've not mentioned there is cache. The CPU, as well as being able to communicate over the memory bus to the system memory, also has its own cache memory. And this is something else we've seen over the years. The cache memory that's available to the CPU has grown drastically. So whereas an older CPU might have a very small cache, modern CPUs have a much larger cache. And that means that when you're executing your logic, if you can use that cache memory, then you can be a lot more efficient because that cache memory is directly on the CPU and it's much, much faster. Now, these architectures continue to evolve, but typically the state of the art today is to have as much silicon as possible on a single chip, and then that chip effectively forms your complete computer. You still need a separate system clock. So the system clock is the thing that produces the clock cycles to tell when things to operate. Some devices operate faster than the system clock. So for example, RAM these days, RAM can operate at multiple clock cycles. So you've got this concept of multiple processor cycles or multiple RAM cycles off a single clock cycle. The clocks themselves, of course, they're also a lot faster. And another thing about the clock is increasingly with modern CPUs, the clock is variable because the CPU itself can change its speed according to what workload it needs. So when the computer's heavily loaded, it will be running at a higher speed than when it's lightly loaded, in which case it can slow down, and that reduces the power consumption and reduces the heat. So there's a lot of other aspects here which are getting a lot more complicated in modern devices, but all of this is helping us by improving the performance we can get from these modern components. So this is what we see today on smaller embedded systems, and also this is an example of, from the previous slide, what your current system might look like. It's what we call system on a chip. Particularly for embedded computers and smaller devices, often those from ARM. ARM Holdings have various designs which you can get chips made against. And in this case, what you'll see is all the components are integrated on a single substrate in a single package. It might actually be multiple substrates. So for example, you might see multiple level chips, but the idea is now you've got this single device which pretty much does everything. So for some embedded devices, there's effectively only one chip on the board. It's for CPU, it's got its own graphics processing, it's got all the memory interfaces, it's got all the third party interfaces like Ethernet and audio and USB and graphics and so on. So the benefit there is, although the silicon is a bit more complex, the overall system is considerably simplified. Now, generally with these system on a chip applications, we can't get quite the high speed, but we don't really want to. These are used for embedded applications where we don't need very high performance. So you might see this in a network switch, for example, or a router or a gateway. You might see it in a lower powered edge device. So what we can do with these devices is, we can have everything in a single chip, easier to manufacture, lower power, but if you only need that lower amount of power, that's fine. So here's an example of a traditional motherboard. Unless you're building a gaming computer, you probably won't see one of these. They're still used inside some larger computers like servers, but generally with the server, it's all pre-configured from the vendor. You might see this if you were open up a workstation or a larger desktop computer. But again, what you'll find in more modern computers is the motherboard is now shrinking down and has fewer and fewer expansion capabilities. So unless you're building your own gaming computer, you probably wouldn't really see this. But what you can see in the middle there, you can see the CPU socket. So that's where the CPU will be plugged in. On top of that CPU socket, there would be a heatsink. And if you're building a gaming computer, that heatsink could be a fairly substantial lump of aluminium with various vanes. And then it might also have one or two fans bolted onto it as well. And that heatsink is the primary way of removing heat from the CPU when it's under power. What you might also find is in very advanced systems, you might find that CPU heatsink is the case itself. I've seen that for various industrial PCs where you use the case of the industrial PC as the heatsink. And you can also get some advanced applications which use water cooling. So what you'd have there is you'd have a device which transmits water, and then there would be pipes which go to a radiator, and then the radiator is often fan cooled as well. So a variety of different cooling mechanisms depending on what sort of system you want. Immediately next to the CPU underneath, you can see power conditioning. So there's a set of transistors which are used to give the CPU its different voltages. Voltages, we've seen a big variation in voltages over the years, coming down from higher level TTL voltages of 5 volts, then coming down to more like CMOS type voltages of 3.3 volts. And the modern CPU can run at very low voltages. And the CPU will actually control what the voltages are. So when it needs to run faster, you might boost the voltages. When it's running a bit slower, it might not need that boost, so the voltages can be reduced. And again, if you're into computer gaming, these aspects you can control. You can control the power to the CPU along with the clock speed to define how fast the CPU actually works at. Now, moving up again, there's a battery there. You typically see a battery which is used for maintaining the BIOS contents. A modern BIOS might use flash, but older BIOS use a battery-backed RAM, and that would power the real-time clock. So there's a battery there, typically like a coin cell battery, that you need to replace every 5 to 10 years, depending on the unit. You move around, you can see RAM sockets. So there can be multiple sockets depending on what sort of computer you've got. Again, if you're building a gaming computer, you probably have 4 RAM sockets, and you would either use one or pairs of DIMMs, or you could use multiple DIMMs depending how much memory you've got and how much money you've got to be able to afford the memory in the first place. Memory prices have come down significantly over the last couple of years, and it's quite feasible now to have large amounts of RAM to control your computer. You don't want too much RAM because it would be wasted, but you want enough RAM to be able to cope with your day-to-day operations. Otherwise, the computer has to offload to the hard disk, and that significantly reduces performance. So typically 4 sockets, but what you might see on an industrial PC, I've seen this on rugged computers, you don't actually see the RAM sockets. Instead, the RAM is actually soldered directly onto the board. And you also might see the CPU is soldered onto the board as well. This is also common with laptops. But one of the reasons for soldering onto the board is it reduces the costs because you don't need those connectors. But it also improves the ruggedness of the device because everything is soldered and it can be firmly clamped down. It also takes less space as well, which is important if you've got a laptop and you're looking at portability and weight. So multiple reasons why devices might be soldered rather than socketed. Of course, if it is soldered, it means it's non-upgradable. But if you're looking at something with a laptop with a shorter life, or if it's an industrial PC which has a dedicated life and isn't going to be upgraded, then that's fine. Now on this particular motherboard, moving around the bottom here, we've got all the peripheral interfaces. So there's connections for sound, there's connections for monitors, there's connections for USB. This one is quite an old motherboard. It's got these old round sockets for legacy keyboard and mouse. You wouldn't see that today. You probably wouldn't see that D-pin, D connector either. That would always be USB today. And the audio might be there. Again, some systems use USB, although the best audio often comes from a 3.5mm jack, but that depends on what you're connecting to. Now, another aspect we've got here, keep going around to the right as we move anti-clockwise. There's a header, which is used for front panel connections. So that would include things like outputs for LEDs, inputs for like a power button and for a reset button. And there may be additional connections there depending on what's required. Again, if it's an industrial PC, that would all be pre-wired, and of course if it was a laptop, that would all be built in. So you might not see that, but again, if you're building your own computer, you would. Now in this particular motherboard, we now have multiple PCIe slots. So there's full-length PCIe, which might be used for some peripherals. There's one there, you see the blue one, and not the next one immediately, but moving to the right, there's another one which have got those connectors on. They're probably used for graphics cards. Graphics cards use a higher speed version of PCIe. So the very small PCIe slot you see there, the one that's not very long, is probably an X1 socket or a ×1 socket. So that has limited bandwidth, but that would be fine for plugging in, say, a sound card. And then on the bigger, longer ones where you've got ×16 or X16, that gives you much faster bandwidth to plug in a graphics card. And in a really high-powered computer, particularly for gaming, you might have multiple graphics cards as well. So that's why there might be 2 graphics PCIe slots, as well as other slots for other reasons. Now you may see PCIe slots in the industrial PC. That will depend on what expansion capabilities it's got. It might be modular, or they might be available based on the fixed capabilities of the system itself. In an industrial PC, those PCIe slots might be used for legacy interfaces, like maybe high-speed Ethernet, maybe Ethernet IP or Profinet or something like that, maybe for DeviceNet, maybe for Profibus, CAN bus. So there might be multiple PCIe sockets there for those legacy connections. Now this particular motherboard, it's also got, moving around to the right again as we go anti-clockwise, it's also got a legacy PCI socket. So this is an older version of PCIe, of PCI rather, and this is used for older versions of boards. So you might see that in industrial PCs, but I would say these days you're probably not likely to see that unless it's a specific computer board that is designed to have that PCI interface for legacy boards. These days most things have migrated to PCIe. So PCI, you can see it's got a different format. It's a slightly bigger connector. It certainly doesn't have the same level of throughput, but you might see that on some legacy devices. Now keep going around to the right, there's more power conditioning. You've got the power supply connector, and what you'll see next to that power supply connector, which is a pretty big beefy connector, that's got the power conditioning for the motherboard itself before we get down to the final power conditioning for the CPU. So the power conditioning for the actual motherboard itself, that includes voltages like 12 volts, plus or minus 12 volts, which can be used for some devices. The 5-volt rail, maybe 3.3-volt rail as well. So those power conditioning devices are used for the actual power for the motherboard before it's split off to the individual devices. One thing about the power supply is, with that power conditioning, the quality of those power conditioning chips and devices can make a significant difference in the quality of the motherboard. It can affect performance, it can affect stability, and it also affects the life of the motherboard as well. So maybe for a gaming computer it's not so important because it's not on 24/7, although I know some gamers who maybe are playing the computer games a lot, but typically power conditioning for a standard device, you would use standard components. But in an industrial device, you'd be looking at choosing more rugged, longer life versions. For example, electrolytic capacitors, which need to have a longer life without drying out, maybe more rugged power converters, more rugged transistors and so on. They would all be required to extend the life of the device. And then the final one, as we come round anti-clockwise round to the top, there's the peripheral interface chip. It's actually underneath that heatsink because that chip also generates heat. But we've here got our peripheral interface chip that's used for things like USB connections and maybe additional connections. And then there might be a host of other connections on this board. So for example, you might get fan connections, you might get connections to a system beeper if that's not already on the board. And there might be jumpers to configure the board, although that's rare now because normally configuration's done from the BIOS. So there might be a lot of options depending on what motherboard you've got and what capabilities it's got. But that just takes you through the function and capabilities of a traditional motherboard. We still see some of these components today. Obviously on the laptop, it's all shrunken down and much smaller for portability and lightweight. And in an industrial PC, it's in there still. But again, shrunken down and made smaller and more ruggedized for the case of the industrial PC, whereas portability is more important in a laptop. So let's move on to CPUs. The CPU is the heart of the computer. It's the one that does all of the processing of your instructions. It interfaces with all of the devices, and it does all of the running of the algorithms and all of the code that you develop. So there's quite a bit of differentiation in CPUs. I'll come on to some of the manufacturers in a minute, but there are multiple manufacturers. Different manufacturers have their own different architectures and manufacturing processes, which can affect the final configuration and capabilities of the CPU. Also affects the price, of course. But the biggest differentiator that people look at next, once they've chosen a particular vendor, would be based around the processor speed. Typically, a higher number of megahertz, or these days gigahertz, normally means the CPU is faster. But also the architecture can affect the processor speed as well, and also the number of cores, and are we doing hyperthreading. So for example, you might have a process which runs on a single core, in which case the faster the CPU speed the better. But a lot of modern applications distribute the processing across multiple cores. So it might be better to have a slightly slower CPU with more cores compared to a single core processor that's got a higher speed, because you could distribute your application across those multiple cores. Now hyperthreading, this is a way of having one core run two different threads at the same time, so it effectively turns the number of cores you've got, it effectively doubles that number of cores by using what we call hyperthreading, but it's not quite as efficient as having an additional core itself. Now the architecture, these days the architecture question has pretty much gone away. Most modern computers are what we call 64-bit, which means they're capable of processing native 64-bit values. Older computers, when I started in the industry, we had 8-bit, this is a long time ago. We moved on to 16-bit, then we grew to 32-bit. Most modern computers today, with the exception of maybe some older embedded devices, are normally 64-bit. Now, having a wider memory architecture like that, it does mean you can access more memory, which is good. Having the bigger numbers, that also helps you, but it does actually reduce performance slightly. So you might find that in some applications, a 32-bit computer is faster than a 64-bit computer, particularly if you're only using 32-bit type calculations. But these days 64-bit is catching up, 32-bit is going away, so most modern computers would be 64-bit. And to put it in perspective, if you think of a 64-bit number, if you're playing golf and you use a 32-bit system, you could calculate the golf hit and you could work out how far that golf ball could be hit and what sort of resolution you could get. So if you could really hit the ball fast enough, using 32-bit maths, you could get the ball to Pluto and you could calculate the distance across that huge distance. But if you go to 64-bit, you wouldn't just be able to get to Pluto, you'd be able to hit a hole in one. So if the hole was on Pluto, 64-bit would give you the ability to calculate a hole in one, even with the golf ball starting on the Earth and ending up on Pluto, whereas 32-bit would really only just get you to Pluto. It wouldn't get you that last level of accuracy. So there is a bit of an impact on having 64-bit, but with modern processors, as they get smaller, that's effectively going away, and you gain a lot in that additional accuracy and also the larger memory capability that 64-bit gives you as well. Now, another aspect of modern computers is pipelining. In the olden days, what used to happen was the CPU would execute one instruction for every clock cycle. And that was it. So if you had a 1 gigahertz computer, it would do 1 billion operations per second. Now you can add more cores, so a dual core 1 gigahertz CPU would be able to do 2 billion operations per second. But the idea of pipelining, you can now start to queue multiple instructions through the CPU at the same time. So instead of just doing one thing every clock cycle, you could now be doing 4 or 8 or even more operations at the same time. And it's like a pipe, it goes in at one end, you process on each clock cycle as it goes through the pipe, and the result comes out at the other end. It's actually a lot more complicated than that, and there's things like branch prediction which comes into it, and other things. But the idea of pipelining is the more pipeline you have, the more efficient your computer can be, because it can do more things at once and more things every clock cycle. Now, coupled with that is cache size. Cache size is important. I mentioned cache. Cache is the local memory that your CPU uses. Generally, the bigger the cache, the better, but more cache costs more memory. Cache is very high speed local memory. And these days, we talk about large megabytes of cache, particularly at the L3 level. There's various levels of cache. L1 is the smallest, because it's the fastest and the most expensive, but it's the closest to the CPU. L2 is sort of in the middle, L3 is slower, but still L3 significantly improves the performance of your CPU. So having big cache helps. Branch prediction, that's sort of related to pipelining, but also in terms of looping. So what happens inside your computer is, as you're processing your instructions, at some point you'll be taking a decision, and you will either decide to do one thing or another thing. So what a modern CPU can do is it can actually predict what you might do in future, and if you can predict correctly which branch you're going to take, that can make your processor more efficient. Because, for example, if you're driving to work, if you know you're always going to be turning left at each junction you get to, you can predict which lane to be in, and you'll get there faster than if you're waiting to the last minute and then you have to switch lanes. So it's the same in these CPUs. Being able to predict which branch to take can offer performance improvements and make you faster. Now, instruction set support comes into it. Intel and other vendors, they have different levels of instruction they support. Embedded GPU, this can also be something that you want to look at. If you're doing a lot of graphics processing using the simple CPU, a better GPU helps. And we even now have a name for CPUs which have a combined GPU. We call them an APU, so more of an advanced processing unit rather than a separate GPU and CPU. And another part of that is NPU. NPU is a neural processor unit, and that's used for processing artificial intelligence loads. Now, something that's improved dramatically over the years is the transistor size. We now measure transistors on the CPU in terms of nanometers, and we're getting down to some very small nanometer sizes. In fact, the next level, we might even be talking about angstroms, which are fractions of a nanometer. But typically, a modern CPU will be down at anywhere around 7 to 5 nanometers or maybe less. Now, this isn't really something you can impact so much. It's related to the architecture and the manufacture and the generation of CPU. But generally, the smaller the transistor size, the faster the CPU can operate, and also the amount of power can be reduced. And also, because the transistors are smaller, you can fit more transistors on the die, which means you can have a more complex CPU. So smaller nanometer sizes do help when you're thinking about the amount of cache, you're thinking about the number of cores you've got, and also, as I mentioned, it relates to the speed and it relates to the power as well. Voltage and power, that relates from there as well. Voltage, probably not so important because you don't really have much control over that as a user. That's a decision that will be made for you by your vendor. Could be important if you're overclocking. If you're doing computer gaming, you might want to overclock the computer. So what you do with overclocking is you're increasing the processor speed, and then you might also need to tweak the voltage, because as the speed goes up, you might also need to increase the voltage so that you don't get corruption or instability of the CPU. Note that can reduce the life of the CPU. Higher voltages and higher speeds can generate more stress. And if you're not careful, it is possible to destroy the chip. If you go too fast with too high voltages, that can actually destroy the chip, and then it's dead. You'd have to get a new one. Related to voltage and the speed is what we call power. Power is generally measured as TDP. TDP is like the overall power that the package can handle. And you might see that in certain industrial PC designs. Generally, the higher the TDP, the faster and the more powerful the CPU can be. But that's not necessarily what you want. If you need a low power device, then if you've got a high TDP, then you're just wasting resources. So often what you would do is you would look at the TDP and you might want to tailor that to your particular application. You don't want to have a too powerful computer because A, it costs more money, and also if it's using more power, you're wasting energy there as well. So power, TDP, is something that you will see, particularly with industrial PCs, because it's one of the ratings that you have some control over. Now, there may be power management features. Different CPUs have different power management features, usually defined by the CPU manufacturer themselves. But often what you'll see is you might see overclocking capabilities, probably not in an industrial PC, but certainly in a consumer or a gaming environment, you'd have some control over power management. Power management is also operated by the operating system as well, so there may be different power modes depending on what you're trying to do with your computer. For example, with a laptop, you might find that when you're plugged into the mains, you could run in a performance mode. When you're running off batteries, you might want to reduce the amount of power so that you'd use the power management features. And when the battery gets very low, you might want to switch off certain functions. So those power management features can help you under different environments and different operating routines. Something else that's important to the vendor who's making the computer, but less control for you as a user, is the package and socket type. Again, some modern computers, the CPU is soldered direct onto the board, but for other ones, you might want to be aware of what the package type is and what the socket type is. Particularly if you want to upgrade the CPU, you need to make sure that socket type is one that's going to have a long life. And if you do want to upgrade, of course, your new CPU will need to be able to fit in that original socket on your motherboard. Temperature rating, here's something else that you might need to be concerned with. Typical consumer grade equipment is rated at 0 to 40 degrees centigrade, maybe a bit higher, but when you're looking at industrial computers, you might want to go to 0 to 60. You might even want to go to even higher and lower temperatures. So a very rugged design might be minus 40 to plus 70. And if you're looking at some applications like automotive, the temperature goes higher still. It's difficult to go below minus 40 because at minus 40, that's where the actual electronics stops functioning. But you certainly might want to go higher. I've seen some industrial devices where the higher level operating temperature is plus 85 degrees C. But that's pretty rare. Normally, the maximum would normally be 60 or maybe 70. Of course, price is important. The more faster the processor, the more number of cores, the larger the cache and so on, generally the price goes up. And the final thing there is long-term availability. Again, that's something that you have to rely on your vendor for, but there are some versions of chips that are made for longer than others. So what you'll find with a consumer grade chip, it's maybe only made by the manufacturer for 1 or 2 years, and then it will be replaced very quickly. So if you're buying an industrial PC, your vendor will normally negotiate with the manufacturer of the chip, and they will produce or use a chip that has a much longer life, and it's specifically intended for these more industrialized environments. So what the vendor would normally be looking for is a commitment from the manufacturer for at least 5 years supply, and then they might buy more to keep them going for longer extended life. But ideally, what you'd be looking for is a chip that's going to be made for 10 years. And the chip manufacturers do make these chips for this long term, but generally, as they get older, the prices go up. But you may also be exposed to unexpected discontinuation of chips if you're using something that's very old. So you're also relying on your industrial PC vendor to manage that long-term availability. It's not just down to the individual chip manufacturers. So there's a lot of aspects there. Ultimately, that might be out of your control, because if you're buying a new industrial PC, you may only have a limited choice from the vendor as to what you want. But there's still quite a bit of differentiation. You have different levels of computer size, different levels of performance, different levels of price. So there's still quite a lot of flexibility there when you're actually choosing your industrial PC. So there are some CPU implications for embedded devices. First of all, as a CPU gets hotter, generally it slows down. Now, you'll see this in a gaming computer. When it gets really hot, you'll see you start to lose frames. You may get corruption of the graphics screens. Under extreme circumstances, if your chip gets too hot, then the game may crash and the whole computer may even shut down. So a good design is required to reduce or eliminate this, but of course this adds costs. And this is one of the reasons you'll see industrial PCs are quite expensive, because the vendors and designers of those PCs, they are managing that CPU design so that the CPU ideally keeps running as fast as it can all the way up to the maximum temperature. So to do that, it's possible, but you need big heat sinks. You need special control over the voltages and the speeds in the first place. You might even end up underclocking a CPU, so that in order to avoid hitting those maximum temperatures, you might want to avoid hitting the maximum speeds. So a lot of implications there, but that's certainly something you're very concerned about. If you're in an industrial environment, if the temperature goes up, you don't want to lose control of your application. So you need to make sure your design will run as fast as possible at as high a temperature as possible without any degradation. Again, maybe less important for HMI SCADA application, but if you're relying on your industrial device for your control, it's very, very important it can run at full speed at maximum temperature. Now, what I see is many embedded applications are not optimized for multiple cores. Multiple cores will help overall for parallel operation. So you might have a dedicated core for networking, you might have another dedicated core to run some operating system tasks, and then you'd have cores left over to run your algorithms. But this is one area where you can look at a device and think that it has very high performance, but if your application is only using a single core, you're actually constrained by what that single core performance is. Now, in some cases, using a single core, you can get very high performance from that single core, but in other cases, you might find you're quite constrained because the chip just isn't designed to run multiple cores at the same time. So you do need to take care of that, and that might require that your embedded application does need some optimization. Ideally, the more cores you use, the more your load is spread across those multiple cores, the faster it will run overall, and without having to increase the temperature too much. Another aspect, of course, higher speed, higher megahertz or higher gigahertz these days, that means more power consumed, that generates more heat, that also means more cost. What I see in a lot of embedded systems is, we can reduce the amount of power consumed by maybe running a command line operating system rather than run a graphical user interface. Or maybe we run a web server and we have a separate computer that's used for configuration. Those are great ways to reduce the amount of performance we need by moving off some of the capabilities away from that CPU. Any time you're doing anything that's associated with graphics, then that can mean that you're going to be using more power. And again, you might want to optimize your application as well, based on what sort of performance you've got and what capability you need. And I'll talk a bit more about optimizing later on. There are life cycle issues. Newest designs may not be proven in use. Some people prefer to use something that's been around for a year or two or maybe more. Now, with a modern consumer chip, this isn't really possible. If you go to a modern computer manufacturer like Dell, they'll have their current devices, and then they may have the previous generation, and that's it. You've got maybe 1 or 2 years of history there. You can't buy anything older. Everything is based on the latest chips. But if you're in an industrial application, you might be looking at something that's maybe 2 generations behind, and that's fine. One of the great things about these industrial versions of these chips is they do have a longer life. Of course, the vendor themselves will do a lot of care to make sure that these chips are capable of operating correctly. But what it does mean is that typically, if you're looking for an industrialized device, it won't be the very, very latest generation. It will be 1 or 2 generations behind. And that's fine, because if you were using the latest generation, you might find there are unfound bugs yet. You might find there are cybersecurity issues. You might find other issues. If a chip is a couple of years old, then it's likely that those sorts of issues will already have been found. Of course, you do need a vendor with a commitment to long-term supply. If you wait too long, then that CPU and the other chips could be near the end of their life by the time you choose them. So again, if you look at the commercial arrangement for chips, normally someone like Intel will develop a chip. It will be brand new in development for a year, then it will be active for a year, and then it will be moving towards end of life for next year. So it's got about a 3-year life. So if you were doing that as an industrial computer, if you were waiting 2 years and then you start to buy that computer, it would already be at the end of life. But as I say, luckily with these industrial versions of these chips, they do tend to have a lot longer life. So that's less of a problem. Intel is the dominant manufacturer of desktop and server CPUs, and possibly the most well-known developer and manufacturer of CPUs. They were the original developer of the current x86 and x64 architectures, which have been copied by other manufacturers, but with Intel's dominant position, they were able to set the standards that other people had to adopt. You might also have come across the idea of Wintel. Wintel is the combination of Microsoft Windows and Intel CPUs, which was very common in the 90s and early 2000s, as these systems worked together very well. Now, the current range is the core range, and you have to be careful here because Intel do keep changing their naming based on different versions of the CPUs and whether it's a particular target, such as is it for consumer, is it for gaming, is it for commercial, is it for server markets? But the structure does keep changing quite frequently, so it can be quite difficult to keep up. But if you look at the core range, which covers desktop and mobile, and then you've got Xeon, which is the server range, and there may be others. So desktop and mobile. Mobile is also used for industrial PCs because they're low power but high performance. So you have the i series, and the i will probably go soon. The Core i9 or the Core 9 series gives you the highest performance. That's for enthusiasts and for high-powered workstations. Probably not seen in industrial PCs. Then we see the i7, which is high-end. i5 is mid-range, and i3 is low-end. Now I say low-end, it's not that low-end. Even an i3 today has quite a high benchmark performance. We also see M for mobile, although you can now get 7, 5 and 3 in mobile ranges. And then we also see Celeron for some embedded applications as well. But I think the Celeron is being overtaken by the i3. And then there are some other Intel models coming up as well that you'll also see in embedded applications like U300. Servers tend to be a lot more expensive because the chips have more cores and higher levels of cache. They also often include support for error checking and correction in the memory, although you can get that with some of the embedded CPUs as well. So typically with the server you're looking at E7 is the high end, E5 is like a data center version, E3 is standard. But again, there's a lot of overlap between these different CPUs, and depending on what people are doing, are they focusing on performance? Is it more for storage? Is it for user functions? There's a wide variety of different applications that might be used, and which you might use different CPUs. And for embedded, of course, you've also got the idea of a CPU load. If you're doing analytics, if you're doing maybe some sort of processing on a continual basis, particularly if you're controlling an application, then you've got slightly different requirements there as well. Here's a brief timeline. Again, can be difficult to keep up. because Intel typically have a new CPU every 1 year to 18 months. That they operate on like a tick-tock approach. So 1 year you will get the tick, which is an upgrade on one part of the CPU, and then the next year you'll get a tock, which is like the other part. But each year there are improvements in performance. Sometimes it might be worth waiting a couple of years, depending on what your requirements are, because it can be the tick or the tock offers you greater performance. And as we mentioned before, looking at the size of the CPUs, that continually comes down, and generally the size of the CPU, the smaller the transistor, the more performance you'll get and the higher the processor speeds can get. But you also need to look at the number of cores, you need to look at the overall speed itself, and then you also need to think about cache, level 3 cache in particular. All of those can make a big difference on performance depending on what sort of load you're trying to do. So if we look at ancient history, this started in the 1970s, actually probably before then, but the first x86, what we would call a proper Intel CPU like the ones we have today, the first x86 16-bit processor, that came out in 1978, and that used a 3 micrometer process. 1985 we saw the 8386, which was the first 32-bit x86 processor, and now the die size has shrunk down to 1 micrometer. That's for the transistor size. 1989 we saw the 8486, which had an integrated floating point processor, and now we're down to the nanometer sizes for the transistors. Pentium first came out in 1993, and there are a variety of different Pentium versions. Celeron came out in 1998, which was the first low power CPU, and then we're getting down now from 250 nanometers initially down to 14 nanometers for more recent versions. NetBurst in 2000 was the first 64-bit CPU architecture, which also included hyperthreading. So hyperthreading is a way of a single CPU to run multiple threads at the same time. So it improves the efficiency of the CPU quite significantly, but without increasing too much the price or the complexity of the underlying die that you create. Pentium D came out in 2005. This was the first CPU with multiple cores. And then by 2007, we got the first generation Core CPU, the Core 2 Duo. And then that Core 2 Duo is a significant step up from the older Pentiums. Again, smaller transistor size, bigger cache, but significantly improved performance. With these core processors, where we see successive improvements over the years, from Sandy Bridge for second generation, through all of these different generations. More recently, Raptor Lake, which came out in 22-23, Meteor Lake, we're now down to about 5 nanometers, and from 2025 onwards, again, the nanometer size is shrinking, the CPUs are getting faster, the cache is getting faster and bigger. So with these names, by the way, these are internal Intel names. Generally what you should refer to them is the actual generation of the CPU. For example, talking about Raptor Lake can be confusing because Raptor Lake covers both 13th and 14th generation. So probably better to refer to the actual generation of the CPU. And that generation number is often part of the CPU name. So for example, a 13th generation Intel CPU might be an i7 13800. So the 13 indicates that's a 13th generation Intel CPU using a 7 nanometer process. And again, very recent, very powerful, very fast. But again, each subsequent year or two, you're continuing to get significant improvements. So the way to keep up, keep an eye on the trade press. That often has articles about what the latest CPUs are. You can also investigate the web pages of the vendors themselves, so both of Intel, but also of the people that actually generate and make computers. They will give you updates on these. But often, it's a constraint when you buy the computer. You might not get a full choice of what CPU is installed. You might instead more focus on what the application is. So you might buy an industrial PC, you won't get too much choice over what the CPU is, but what you'll be looking at more is how the vendor might guide you, and also what sort of applications the IPC is intended for. And then the CPU comes with it based on what that vendor offers. Certainly, the more recent the CPU, the faster it is. Also, the smaller the transistor size, again the faster, and again, that level 3 cache size goes up as well, which also improves performance. And then you can compare by total TDP, how fast is the CPU in terms of its power, how fast is it in terms of its maximum gigahertz rating, and then you can also compare the cache sizes as well, and the number of cores, of course, depending on what your application is. So AMD is the other manufacturer of desktop and server CPUs. Becoming popular, there's often a leapfrogging type approach from AMD to Intel. So you'll see an Intel revolution one year, and the following year AMD catch up and overtake, and then the following year it goes back to Intel and so on. So it's worth keeping up with both of them. Some vendors prefer AMD because they are quite good in certain niches. Generally not quite as fast or powerful as Intel, but they can be significantly cheaper. So if you're an enthusiast and you're building your own computers, AMD might be quite interesting for you with the current Zen series based on Ryzen CPUs. But again, there's this continual leapfrogging, so it can be quite hard to keep up. Where AMD are also good is with embedded graphics. AMD acquired ATI, which was a well-known graphics company, and they're also known for GPUs as well as the actual CPUs. So what AMD are also good at is, if you're looking for an APU, an advanced processing unit, rather than just a pure CPU. So the APU is a CPU which also includes the GPU, so they can be more powerful. So often I find, if you're more concerned with graphics performance in a single chip, then AMD often beat Intel. But there's other considerations. I do find that AMD consume more power, so maybe not quite so useful for embedded applications. But again, it's all about timing. What I say this year might be completely different the next year, and then it might switch back for the year after. So yeah, worth keeping up with the press and of course what your vendor can offer you to understand which is the best. Now the timeline for AMD is a bit more complicated than with Intel, because Intel have their generations. With AMD, they sort of stopped at the Zen models with the Zen core in 2017, but they continue to improve the Zen range, and there are new models coming out, still called Zen CPUs, but each successive year has, again, smaller nanometer die sizes and transistor sizes, more cores, faster execution, so it needs a bit more attention to understand what you're getting. But again, a long history. The first AMD in-house processor, before that they were having them manufactured externally, that was the K5 way back in the mid-1990s. The K6 added some additional functionality with 3D Now for 3D graphics. The Athlon was the first CPU to reach 1 GHz way back in 1999. And then you had the K8 Hammer, which was the first AMD 64-bit CPU. The Athlon X2 was the first AMD dual-core CPU, followed by the Phenom in 2007, which was their first quad-core CPU. And then you had FX and Bulldozer, Pile Driver, Steamroller, Excavator. As I say, currently we're looking at the Zen core, Ryzen and Athlon models, but using Zen. They can have up to 128 cores, but that would be more for a server focus. And again, these days we're probably looking at smaller than 7 nanometer sizes. AMD also do a lot of lower processor sizes, which are used for embedded applications. For example, 2011 they released the Bobcat, which combines CPU and GPU into APU on the 40 nanometer process. Jaguar, which was used in the PS4 and the Xbox One, a 28 nanometer chip generated in 2013. And then there are various other chips which are in their lower powered and embedded applications. AMD, as well as offering x86 CPUs, they also offer some specific chips for use in embedded applications based on alternative architectures as well, besides x86 and x64. So you might also come across ARM. ARM Holdings don't manufacture chips, but what they do is they design architectures which are licensed and manufactured by others. So you can get like standard implementations, which is the Cortex implementation, but it's also possible to get a customized implementation as well. The way ARM generally work is that they implement their designs as a system on a chip. So what you can find is, as well as having the CPU, that one chip design can include RAM and it can include specific interfaces. And ARM is very common in low power embedded applications and mobile applications. So you might find that if you have a low power requirement for maybe a gateway, it could be that there'd be an ARM CPU which is adequate for what you want. Now, ARM is rarely used on desktops because it's not x86 or x64 compatible. So these days it won't run Windows, although Microsoft is moving into the ARM space. So that may change in future. But if you're running an operating system like Linux, then that's fine. You can get a more efficient operating system, which is what Linux is, and that could cover your requirements and allow you to use a smaller, lower powered CPU with less RAM, but still achieve whatever your goals are for your application. Yeah, particularly, as I say, for things like gateways, maybe for low speed data logging, maybe for low speed analytics. In that case, ARM could be a good choice. So we've covered some CPU technology. Let's move on to some more of the technology that goes on around the CPU and the computer, starting with the heatsink. Now, CPUs generate a lot of heat, and the heat is concentrated in a very small space. So what the heatsink does is it takes the heat away from the CPU, and sometimes that can also take heat away from other components as well, which can also run very hot. The heatsink dissipates it into the environment. So generally what you find in commercial PCs and older industrial PCs, the heatsink is often a large aluminium block that mounts onto the CPU. There would be vanes for greater airflow. Modern large heat sinks can consist of multiple vanes, each of them very thin in like sort of layers, and then there's airflow through those vanes, and what happens is the air takes the heat away from the vanes and then dissipates out into the wider environment. You also see heat sinks with heat pipes. Heat pipes can be used to better transfer heat from the CPU to the heatsink. What the heat pipe does is, it's a bit like in your fridge, there's a heat mechanism, a heat transfer mechanism based on liquid inside pipes. So the liquid heats up and turns to a gas and then moves to another area of the heatsink, which can then give better heat transfer. And then from that part of the heatsink, that gas cools down back to a liquid, and you get this continuous circulation, which gives you better heat dissipation than just using pure metal by itself. Now, in an industrial PC, you probably don't want a fan, but in many commercial applications, you will find a fan. What the fan does is it forces air over the vanes, and that improves their effectiveness rather than just relying on ambient airflow. Now, in modern industrial PCs, what you might also find is the enclosure is also the heatsink. So there's no fans. Fans have an issue that they're unreliable. A fan might be fine in a commercial environment where you're running 8 hours a day, 5 days a week or 6 days a week or so. But when you're running 24/7, your fans have a problem that they will wear out. And even a really well-engineered fan might seize up after anything from 3 to 5 years, which is less than the expected life of our industrial PC. So even the most reliable fans probably aren't reliable enough for an industrial PC, and you'd need to think about some sort of maintenance if there was a fan installed. So what you can find is in the modern IPC, they are made of very big solid chunks of metal, and that chunk of metal is the heatsink itself, which takes heat away from the CPU, and then the enclosure would be vaned to allow airflow, and then you may also have special requirements inside the IPC to spread the heat, so you do need a heat spreader, and that ensures a good thermal connection from the CPU and other components to the heatsink itself. So there's a lot of special technology that goes on there, although the heatsink idea is quite straightforward, but you're into things like thermal transfer paste, maybe heat transfer pads, maybe special heat spreader technology. There's the design of the heatsink itself. There might be the fans as well. If you're into a computer that does need fans, those fans might have a particular design. So there would be different sizes of fan, different speeds of fan. And in a modern computer as well, the fan speed would be controlled by the CPU. So when the CPU is running faster, the fan has to speed up. When the CPU slows down and isn't generating as much heat, then the fan can slow down as well. So lots of impact there, but again, that's normally taken care of by the vendor, and it doesn't need too much addressing by the user, except to make sure that you have got sufficient airflow. So sometimes that might mean if you're putting an industrial PC inside some sort of cabinet, you may need to install fans in the cabinet itself in order to get that correct airflow. And it also might mean that you need to make sure that you've got specific airflow as well in terms of vents in the enclosure to allow for airflow. Again, there's quite a bit behind heat dissipation inside the cabinet that I'm not going to go into, but if you really get into it, that may need some sort of consideration. We also mentioned earlier the mounting of the industrial PC. If you're mounting an industrial PC on a DIN rail, then you haven't got a very good connection to the actual backplate of the panel itself, so that the panel that you install on can also become part of the heatsink. So if you've got a very large enclosure with a solid metal panel, if you can bolt the industrial PC directly onto that panel, that can also form part of the heatsink as well. Now, I briefly mentioned chipsets. Let's look at that in a bit more detail. A chipset is the additional chips that are required to connect the CPU to peripherals. We saw earlier, we talked about North Bridge and South Bridge. More recently, the Peripheral Controller Hub, or PCH, if it was Intel. AMD also call it the Fusion Controller Hub, or the FCH. Now, there used to be a wider variety of chipsets with different features and performance, but more recently, CPU vendors have started to mandate a particular chipset for a particular processor. So there's a lot less relevance of the chipset today, as the chipset may also be combined with the CPU or the APU or the system on the chip. But you will find with some CPUs, there's a choice of chipset which give you different price points and performance levels. Again, this can be quite interesting if you're building your own gaming PC, because what you'll need to do is you'll need to match your choice of CPU with the appropriate chipset, and then you can choose a chipset that either gives you a balance of performance versus cost, or you might decide to go all out and spend a lot more money on a more powerful chipset. It used to be that the chipset had quite an impact on performance, as much as 10% or more of the overall performance of the system. But generally these days, with the modern chips, the chipset makes a lot less difference. It's probably 5% or less, and in some cases, there's no choice of chipset or only a single choice of chipset, in which case it doesn't really matter. So chipset might need focus, but these days it's very much ancillary to the CPU and nowhere near as important as it used to be, unless perhaps you're building a gaming rig and you really want the highest performance available. So the CPU does the main processing, but what you also need is memory, typically random access memory. And the idea of this memory is this stores the current operating state of the computer along with anything else that's required to understand what your algorithm is doing. So current states, set points, other variables that might be used by your application, they're typically stored in real-time memory, as opposed to disk memory, which is more longer term and more normally used for long-term storage of data and applications. So let's explore memory in a bit more detail. So usually when we're talking about memory, we're talking about dynamic random access memory, or DRAM, or just RAM for short. So what this does is this is storing your data for current operations. Because it's dynamic, it has to be maintained by the computer. So as soon as you turn the computer off, all of that random access memory, its current state will be lost. So the computer has to be powered up. But the dynamic random access memory, DRAM, it is very fast. It's not quite as fast as the memory that's on the CPU itself, so it's not as fast as cache memory, but it is quite fast, and it does control to some extent how fast your computer can be. So these days we often see socketed RAM, so either a dual inline memory module, or possibly in a laptop you might see SODIMMs, which are a more compact version. You can also see soldered memory. Soldered memory is a lot more rugged, but you can't upgrade it in the field. But we often see now in modern laptops and industrial PCs, we do see soldered memory. It's more coverage for shock, vibration. But as I say, the downside is it can't be upgraded. So that means if you buy your computer with soldered RAM, you can't do much about it in future. You're stuck with what you get when you bought it. Of course, for a laptop, soldered RAM is also lighter because you haven't got any additional components. You haven't got the additional PCB that the memory is mounted on. You haven't got the socket that's required. So it reduces the amount of space required and the weight. But for an IPC, the key point there is about ruggedness. Now, socketed memory, of course, that gives you the benefit of upgradability. But the downside is you can add more in terms of costs. You do need the connectors, and it's not as rugged. Yeah, I have seen applications where under high levels of shock, DIMM memory or SO-DIMM memory can actually be knocked out of the sockets. They're pretty rugged, but not perfect. So yeah, again, that's your choice, either socketed or soldered. And in an industrial PC, soldered would be your best choice. And if you're buying a laptop, you need to think about, are you going to upgrade this memory? If not, then soldered is fine. If at some point in the future you will want to upgrade, then you probably want to look for something that's got socketed RAM. Now the memory itself, it does have a speed, and this is determined by the memory clock and the data rate of the memory. What we typically see these days is double data rate memory, or DDR, and double data rate is often exceeding twice now. Double data rate means that you read on both edges of the clock, as opposed to just one edge of a clock cycle. So double data rate means it's twice as fast as a single data rate. Today we see DDR3, DDR4, even DDR5, and what this does is it extends the speed of the memory with much higher clock speeds and more reading cycles compared to the older memory which just read or write on just one edge of the clock. So faster the RAM, the faster the DDR number, the faster the memory will be. That there's a sort of trade-off there, because you can go to faster memory, but eventually your CPU will be bottlenecked, or it will be constrained somewhere else. So how fast the memory you need is partly constrained by what you can actually buy, but it's also constrained by how much memory do you want to spend, and it's possibly not worth spending the most money on the very fastest data rate chips, because your CPU is already constrained by other elements. But generally, the higher the DDR number and the higher the data rate that the memory has, the faster it will allow your computer to run. Now, another option is dual channel RAM. We see this in common systems. You often have two RAM memory modules and they're accessed simultaneously. So rather than just having a single memory chip, you have two operating in parallel, and that also increases the speed. So a combination of DDR memory with dual channel. If that was using socketed RAM, you'd have two DIMMs and both DIMMs would be populated. You also need support from the actual motherboard as well for that. But dual channel RAM is also worthwhile because that can improve memory access as well. Now, besides speed, you can also get error correcting code, ECC memory. This has additional chips, so it costs a bit more money, and it also needs support from the CPU. But the benefit here is if you do get a single bit error, then that can be detected and corrected. And if you get multi-bit errors, that can at least be detected. So for critical applications where it's very important what your memory is doing, then your ECC memory is well worth having. And I would say for industrial applications, pretty much mandatory to have ECC memory. In other applications, it maybe doesn't require that much. I mean, we're talking about very, very small numbers of errors. But in industrial applications where they could cause issues, ECC memory can help us overcome those errors, or at least detect them and avoid operating on invalid combinations of values. The final RAM type is determined by the CPU and the chipset, so you may not get a choice depending on what model of computer you're buying. Particularly if it's soldered RAM, then the memory choice is decided by the vendor. Really, it's only a choice if you're building your own system, then you might choose particular socket types, and you also need to consider price. Memory at the moment is relatively cheap, so you can have large memory types, in which case it doesn't make too much to the final system if you have more memory than you need. But it's not that long ago that memory was very expensive and you did have to consider how much memory you purchased. I would say though, it's always better to have more memory than less. So if you're not sure, always buy more memory than you think you'll need. Particularly if it's soldered. Again, you can't upgrade soldered memory. So if you run out of memory in the future because you've got soldered memory and you can't upgrade, that can make your PC worthless. So think about how much RAM you're going to need, and probably buy as much as you can initially, because it might not be easy to upgrade in future. So dynamic RAM loses its power across a power cycle. Some applications require retentive data, so it is possible to have static memory. Static memory stores its data across a power cycle, and there are quite a few technologies for static memory. Some static memory isn't even static memory. Some static memory is actually dynamic random access memory that's battery backed, and there's continual power to keep the memory updated. But there are also memory types for static memory which will retain their memory across a power fail. Static memory is falling out of favor these days because typically now we can use the storage on the computer to store that static memory. For example, there may well be a hard disk or a solid state disk. So really it depends on how fast you're writing to that static memory. The benefit of static memory, if you've got the right type of static memory, it does have high performance, and also it has a long life. We'll see later, if you write too much data to an SSD, you can reduce its life and cause it to wear out. So depending how much memory you've got and what type of application it is and how much memory you're storing, then often you'd use an SSD, but sometimes there still might be a requirement for static memory. The one big downside to static memory is tends to be quite small and also very expensive. So you would only choose that if you really need it. For example, you might have some critical application where you want to store the memory states of the application and guarantee that as soon as the computer starts up, that's available. If the application is running at very high speed, say millisecond response times, then static memory would be a good option for that, to make sure that memory is stored correctly. But if you're just storing a few values a second or less than a second, then an SSD would probably be adequate. So if RAM memory is used for high-speed storage for operations, we also need slower storage, which can be used for longer-term storage of data and that also stores data across a power fail. So there's two key types of storage. There's a hard disk, or HD, or just disk, and then there's solid-state disk. So there's a bit of contention around solid-state disks that I'll come on to. But I think that argument's going away now. Hard disks, there's almost an end in sight where some major vendors will stop producing hard disks and will go solely to solid state disks. But there are still some benefits of the two different technologies. So typically if you buy a computer today, it's much more likely to have a solid state disk than the hard disk. The idea of the hard disk is this is a piece of technology where you had a rotating plate or plates typically made out of glass or maybe aluminium. They were coated with a magnetic substrate, and then there would be a physical disk head that moved across that disk as it was rotating and would read and write data from the magnetic substrate. So very much an electromagnetic type device. So because it was mechanical, there were issues there around reliability. Bearings could wear out. Because of the requirement for magnetics, then the magnetic field could decay, and it was also exposed to external magnetic influences. But in the early days, hard disk is what we used and was very common. I think today, if you look at the hard disk market, generally with these rotating hard disks, they are still lower cost, although SSDs are catching up very quickly. They have higher capacity, larger disk sizes, although again, SSDs have really caught up. Hard disks themselves, because you've got a rotating media, you have to wait for the disk to rotate round to where the data you want to read is, and you also have to move the head across the disk. So today, generally, hard disks are quite slow to read and write. That can be offset by local cache memory on the hard disk, but now you have an issue that the hard disk needs to be powered up long enough for all of the data writes to finish. Otherwise, if it powered off before it was finished, then you could lose that data. But hard disks with cache can sort of catch up with a solid state disk, but would you really want it to? It's extra technology, adds to the price, adds to the complexity. I think from an industrial point of view, and also from a laptop point of view as well, issues with hard disks is that they have a relatively low temperature range. Typically a hard disk is only operating from 0 to 40 degrees C, and you might want lower and higher than that. Even inside the laptop, you might get temperatures of 60 degrees inside, so that's too much for some of these hard disks. And also hard disks have a very low tolerance to shock and vibration. You've got a physical bearing there, you've got a head that's moving across the actual plate. The head isn't actually touching the plate. There's a very small distance between the head and the plate, And what can happen is if there is shock or vibration to the hard disk, the head can actually hit the disk, and then that can damage the electromagnetic substrate, and that can cause damage to the hard disk itself. And if there's severe shock and vibration, that wears out the bearings as well. So what you find with hard disks is, certainly for industrial applications, definitely phasing out, very rarely used because of this lack of temperature and the low tolerance to shock and vibration. Mounting is also an issue. You can get relatively smaller hard disks these days. They used to be quite big, 5.25 inches, then the size came down to 3.5 inches. This is the size of the platter. They were very big, heavy devices with big chunks of steel or aluminium, which we use for the enclosure. 2.5 inch became popular and was quite small and used in some laptops, or quite a few laptops early on. You can even come across 1.8 inch discs, but they're quite rare because as you shrink down the electromagnetic and mechanical components, the cost goes up, but you don't really get any benefits from a shock and vibration area. Hard disks themselves, they use a serial ATA interface, which is effectively a legacy interface these days and comparatively slow, although the speed isn't important because the disk itself is already very slow. So what we did with hard disks is, to improve reliability, we came up with the idea of RAID. So RAID is a redundant array of inexpensive disks. The idea is you could use 2 or more disks. So you might have RAID 0, where you use 2 disks for better performance. So the idea there is one hard disk and another hard disk in parallel. When you write to the disks or read from them, you read and write to both of them at the same time. So it's a way of effectively doubling your speed at the cost of doubling the hardware and also needing some extra electronics to handle that RAID array. The big downside with RAID 0 is if a single disk fails, then you've lost everything because half the data's on one disk, half the data's on the other disk. Now another option is RAID 1. RAID 1 gives you redundancy, again double the price because you've got 2 disks, more electronics. The benefit is if a single disk fails, then all of the data is also stored on the other disk. But it doesn't give you any improvement in speed or performance, but it does give you a big increase in cost. So then we moved on to things like RAID 0 plus 1, which would use 4 disks. So that's a combination of RAID 0 and RAID 1 to give you redundancy and performance, but at quite a lot of extra cost. You've now got 4 disks, so a lot of extra space, a lot of extra power, and you still need all these special electronics to make that work. So then we had RAID 5. RAID 5 uses an N+1 redundancy and striping arrangement, so you could use 3 or more disks and you get the benefits of RAID 0 plus 1 but from a reduced number of disks. So the data's striped across multiple disks, so if one disk fails, you've always got the data on at least 2 of the other disks, so you've got redundancy there. And you've also got increased performance because you're striping across at least 2 disks as well, but it does need at least 3 disks. I'd say RAID is going away because these days we use solid state disks. So let's take a look at solid state disks. These generally cost a bit more and they have lower capacity, but they're catching up fast with hard disks. It's all very well easy to buy today a 1 terabyte solid state disk, and it will only cost you a little bit more than the corresponding hard disk of the same size. 1 terabyte, that's a lot of memory. That's 1,000 billion bytes. If you're looking at storing a database application, that's a lot of data, could be many years worth. If you're looking at storing images, that could be tens of thousands or hundreds of thousands of images. If you're looking at application data, then a typical application isn't even going to fill a 1 gigabyte, never mind a terabyte, which is 1,000 times larger. So key benefits of the solid state disk is, because it uses electronic components, there's no rotating components, you get very high speed. You get very fast reads because you haven't got to wait for this mechanical device to rotate round to where you need it. You just directly access the memory cell where you want to read from. And the same with writing. You just write to the memory cell and the data's there. From an industrial PC and for mobile applications, they have a high temperature range. You can buy SSDs which can go down to -40 and up to +85 degrees. So they're very good for industrial and automotive type applications. Because there's no mechanical components, they have a very high tolerance to shock and vibration. So ideal for industrial and mobile type applications. There's various sizes available. We start at probably a 2.5 inch, but we don't see many of those today. More likely then it's a mini serial ATA, or the modern interface is M.2, which is a very small size. So if you think about the older hard disks, 2.5 inches, you'd actually have an enclosure which was something like maybe 100 millimeters wide by about 60 millimeters across, and maybe 10 millimeters deep. Whereas if you look at the latest M.2, it's now about 20 millimeters by 20 millimeters, and it's only about 2 or 3 millimeters thick, so significantly smaller. And that's ideal for these compact applications like laptops. But it still has the same high capacity, high speed, high tolerance to shock and vibration, and the high temperature range. We still use a serial ATA interface, although that's rapidly going away. More likely today it will be a PCIe interface, which is much, much faster. And we need that faster speed because the disk is so much faster. We now need a faster speed to be able to get the data onto and off of the disk itself. Now, there are some people who still demand RAID, but generally you don't need RAID with an SSD. An SSD is already so much faster than a hard disk. There's no point in implementing RAID 0. Having two SSDs in parallel, you could do it, but the SSD is already so fast, it can probably exhaust the data rate from your CPU before you need two drives in parallel. For reliability, again, SSDs are very, very reliable. There is an issue that they will wear out over time that I'll come on to, but generally the SSD will have a guaranteed lifespan of so many thousands of hours, typically equating into multiple years, and it will operate for that. If you're really concerned about reliability of an SSD, then the issues there can be overcome by doing regular backups, which might be a daily backup with an incremental backup, rather than actually relying on an online backup. Some people do still use RAID 1, and again, that's possible, but again, SSDs are generally so much more reliable than a hard disk. The MTBFs, the mean time between failures, are orders of magnitude higher than these old rotating disks. So I would say these days, if you're using a solid state disk, you don't need RAID. It will last for as long as the lifetime of your application will, and there are ways that you can size the SSD to make it even more reliable if you need it. So SSD types do come in multiple different types. There's what we call a single level cell, which is where you have one electronic cell for each bit on the disk. These are pretty old-fashioned today. We don't see them much anymore, but the early SSD technology did use single level cell. It was generally very fast compared to multi-level cell, which we'll come on to, but with much lower capacities. Quite expensive because you didn't get that many cells per chip. One of the big benefits of single level cell is a high number of writes per cell, so that the way an SSD works is it's like a couple of transistors which are on the chip, and you write to those, and then you can read them as many times as you like, but you have a limited number of writes before that cell is effectively destroyed. So with a typical single level cell, you can have 100,000 writes per cell, after which it will either fail and you can't use it, or it becomes read-only. Now, initially, single level cell devices were used because they had a good operating temperature range, very often used for enterprise storage and industrial use. But these days, the technology has been overtaken by multi-level cell. So these days we talk about MLC, multi-level cell. Initially there was like dual level cell, but we don't really see that much anymore. Today we see triple level cell or even quad level cell. Big benefits are that they are much cheaper than SLC because you've got multiple cells versus a single cell. So that makes them cheaper to manufacture with higher capacities. They are a bit slower than SLC, but they're still very, very fast. So from a performance point of view, yes, in theory you can make a single level chip faster, but there's no point because the MLC chips are already much faster, and the benefit of the MLC is it can have much higher capacities. Now there is a restriction that you can't get as many cells being written to, so they have a shorter life. So it's maybe an order of magnitude or two almost in terms of the number of writes per cell, maybe between 3,000 and 10,000 writes per cell, depending on the MLC technology. But what we do is, because it's an electronic device, what you would have is you would have a controller chip that wears out the SSD evenly rather than writing to the same cell each time. So although you might only get, say, 3,000 writes per cell, what you would typically do is you would have a high capacity SSD, higher than you need, and also inside the SSD as well, the vendors already fit an even higher capacity still, that they don't report that, but there's actually more memory inside that you're not aware of. And what happens is the chipset performs wear leveling. So instead of writing 100,000 writes to the same cell and then having it wear out, what the controller chip would do is it would write different memory writes to different cells each time you use it. And then also what would happen is that controller chip would keep track of the cells which are no longer can be written to, and the next time you want to write, it would write to a different cell. So that wear leveling significantly extends the life of the SSD. It means the controller chip has to be quite complicated, but there's now multiple controller chips which can do this as standard. We don't even worry about it anymore. You just look at the headline capacity of the SSD, you look at the price, you look at the speed, and that's it. You don't really need to worry about the underlying electronics, because the technology now is at such a state that it takes care of all of these issues for you. So people will say, oh, you can't use an SSD because they only have this number of writes per cell. Well, that's not true. What you can look is at the headline MTBF, and you'll find a typical SSD has a very high MTBF. Often, tens of thousands, hundreds of thousands of hours in real life applications, many years of operation. And I've got devices where it's 10 years old, the original SSD is still working, and there are no problems. And the modern SSDs are even faster and cheaper. So I would say that SSDs have taken over from the older hard disks pretty much exclusively, certainly for mobile applications like laptops, certainly for anything where you need high performance, and for industrial PCs as well, because you can get these very wide temperature devices for industrial use where a hard disk just would not cope. So lots of SSD types. Again, interesting if you want to delve into the details, but these days you're really just looking at the headline performances and capacities, and that's all you need to worry about with the SSD itself. So this is a bit more of a discussion about the so-called issues with SSDs. As I say, I believe all these SSD issues have gone away, but some people have long memories, and in the industrial industry, some people are quite conservative as well. And even today, I still see specifications which call for certain levels of hard disks rather than SSDs, because these specifications, they tend to be written, and then that gets into the standardization of the business, and it's very hard for people to go back and refute and change these specifications. So you can see issues which persist for a long time, but they've been resolved in the industry many years ago. So it's the same for SSDs. That the key issue with SSDs that initially they had a bad reputation with a short life and high cost. That the cost issue has gone away. Costs are now very reasonable compared to a hard disk. And as for the life, people complained about the short life of an SSD, but they weren't considering that there was also a short life of a hard disk due to shock and vibration and bearing wear. These days, even a moderately inexpensive SSD would have a life that exceeds the life of the hard disk. Now, one of the reasons that people still are concerned with a short life of an SSD is that limit to the number of writes, which we talked about in the previous slide. This is overcome with over-provisioning. So over-provisioning is where the vendor installs extra cells inside the chips, or extra chips inside the device, and that makes up for early failures. So you might actually find if you delved into the statistics inside the SSD, there's a technology called SMART, you might find there are failures. But unlike with a hard disk where those failures could be catastrophic, the SSD is actually designed to cope with those failures, and it automatically compensates, and you still get your full capacity for the full life of the chip. The other thing we get is wear leveling. As I mentioned, what you have inside the SSD is a controller chip, and the controller chip spreads the writes over all of the cells to extend their life. So unlike with a hard disk where you can write to each magnetic cell indefinitely, or to maybe an SLC where you've got 100,000 writes per cell, you've got a smaller number of writes, but what you do is you just spread that number of writes over a wider area, and that effectively improves the life of the disk buy a large amount. My recommendation is to look at an SSD and also buy a larger SSD than you need, because that will also further encourage the spread of writes over all cells and further extend the life. Again, with costs of SSDs, this used to be an issue, and I think this is one of the reasons why people were concerned about older SSDs with short life. It's because SSDs were expensive. They chose the minimum size SSD they could get away with. The chance for over provisioning and for being able to do wear leveling was limited because you had limited amount of extra space. So these days I would say think about the size of application you need, buy at least double the size of SSD, possibly even more, and that will double the life because you'll have twice the number of cells, you'll be able to spread the writes over those cells, and that will give you more life than you need. And if you're not sure, then buy bigger still. Again, the cost of SSDs is coming down. So if you think you need 128 gigabytes, buy a 256. But if you're going to do that, think about the cost of ownership over the long life cycle of an industrial PC. You might say, well, let's go for 512 gigabytes. Even if you don't need it all, having the fact of having that extra space will help you with that wear leveling and significantly extend the life of the SSD. Now, there is still one issue with SSDs, and that is that the cells do leak charge over time if they're not powered up. So there is a concept of flash memory. What you'll see in flash memory, which is used in USB memory sticks and SD cards, flash memory is designed to last a long time, but flash memory isn't particularly fast. SSDs are similar to flash technology in some ways, but they're designed to be faster. But the problem with the SSD memory is the cells do leak that charge, and if an SSD isn't powered up for a long time, they can eventually lose their states. So my recommendation is, if you want long-term archival storage, you wouldn't use an SSD for that. An SSD will store data for up to about 2 years without power, but after that it might lose power. So it's not a problem if the system's powered up continually, because the SSD and the controller will manage all of that and keep everything powered up, and you won't lose anything. But if you are turning a device off for a long time and expecting to keep its state, then you might find that it's actually lost its memory over a period of maybe more than 2 years. So that is still one issue with SSDs. But again, if you're buying an expensive industrial PC or a laptop and then not using it for 2 years, you could argue, why did you buy it in the first place? And my experience is I haven't seen this issue of SSD cells leaking charge. So probably because I've never had a device that I've not used for more than 2 years. But that is one thing to be aware of. SSDs are not recommended for long-term archival storage if it's not going to be powered up. Let's just have an example of wear leveling. So if you're considering data logging, let's imagine you had one value per minute coming from your industrial application. That would equate to 1,440 writes per day. Now, if you were writing to the same cell, that would exhaust an MLC SSD in a few days. Imagine you had a 10,000 write capacity. Within about 7 days, you'd have written 10,000 values, and that cell would now either fail or turn to read only. With wear leveling, what you do is you now write across multiple cells, and those writes are distributed by the controller. So instead of now lasting only a few days, if you had a 128 gigabyte SSD with an MLC SSD, that would now theoretically last over 70,000 years at the same write level. So that's how then wear leveling can be used to considerably extend the life of the SSD, because instead of writing to the same cell, you're writing to multiple cells, not all at the same time, one after another at different locations, and that considerably extends the life of the SSD cells. Obviously, you need spare space to do that. So again, this is where over provisioning comes in. Over provisioning is something the vendor of the SSD does for you, and they might not even tell you what the over provisioning is. But also then you would also choose a larger SSD than you need. So if you had, say, a system that's going to use, say, 64 gigabytes of data and the operating system and the application, then again, I would recommend a minimum 128 gigabyte SSD for that application, which is double the 64 gigabytes you need. Or better still, these days you might go to 256 gigabytes, because that would give you even more over provisioning and wear leveling capability. So we've talked about the underlying hardware that's inside the computer. Let's move on to graphics and displays, particularly of importance to people that want some sort of visualization. So anything to do with, say, HMI SCADA, you do need a display, and you need to be able to handle the graphics in order to actually show the operator what's going on and allow the operator to see the state of the machine or process visually. So in a modern CPU, you often have an embedded graphics chip, a GPU. So GPU stands for Graphics Processing Unit. Again, if you look at the AMD terminology, they call it an APU, or have done in the past, an Advanced Processing Unit. But what you find in an industrial PC and many laptops is, rather than have a discrete GPU, which is a separate chip, it's embedded into the CPU. These are very common now. In fact, it's almost difficult to find a CPU that doesn't have an embedded GPU, unless maybe you're looking at the server market or for some gaming applications where it's assumed you're also going to have an external GPU. These embedded GPUs used to be quite weak, but today they're actually getting quite powerful. So for most 2D applications where you're not concerned about 3D visualization, then the modern GPUs will be more than adequate, even for high resolution displays. Even if you're going up to a 4K display for 2D applications, the embedded GPUs are good. And the 3D performance is normally acceptable, but that is actually getting a lot better. So if you're into gaming, you probably still want to use an external GPU, or maybe if you've got some other high performance visualize application, for example, healthcare. But for many industrial PCs now, and for most laptops, you just have a single chip, which is your CPU with embedded graphics. Now, if you want an external GPU, you might want that for high performance applications. So these days that would be particularly gaming, like I say, possibly visualization. If you look at MRI scanners, they do some very complex visualization, and to get the performance you need, then an external GPU makes sense. There is an issue here. You do need an expansion slot because you've got to plug that GPU in somewhere. You do need support from the CPU and its support chips because it uses PCIe. And what you find is those GPUs can be very power hungry. In fact, the GPU can use more power than the CPU does. So often they'll be quite large, they'll have a bulky heatsink, they'll have one or more fans, and they do dissipate quite a lot of heat. So for industrial PC applications, it's very rare to use an external GPU, but it is possible. Now, the other use of a GPU is that it can be used for non-graphics applications by optimizing the process you're doing. Now, typically what a CPU does is a CPU is optimized at doing multiple functions. So it's like a multi-purpose chip. But the idea of a GPU, it has a much more limited instruction set, and it's aimed at processing a lot of the same things over and over again, which is what happens when you have some sort of visualization using 2D or 3D. It just happens that that continuous processing of the same thing over and over again is also what some algorithms do. So particularly artificial intelligence, but also some vision recognition and some other sorts of algorithms, they can also use that GPU processing capability for non-graphics applications. Now, another aspect about graphics is, regardless of which you've got, GPU embedded or high performance, typically the graphics may have its own RAM, or it may share system RAM. So you do need to be a bit careful, because sometimes you might have some of your system RAM is being used for graphics as well. So again, that's something to take care of, is how much RAM do you actually have available depending on what sort of graphics you've got. So particularly with an embedded GPU, the embedded GPU often uses the system RAM, but you normally find with an external GPU, it's got its own RAM. So just be careful. You might buy a chip, an industrial PC with say 4 GB of memory, but you might only find that 3.5 of memory is available because 0.5 GB is used for graphics. But again, RAM getting cheaper these days. So again, normally you'd buy a larger system than you need, in which case that's not so much of a problem. So the graphics inside the system are driven by a GPU, either embedded or external. And then what you need is, you need the actual display itself. So this is the screen that you look at when you're operating the equipment. There's a variety of display interfaces. VGA is an older analog system, rarely seen today. I haven't seen VGA for a long time now. I think several years ago I threw out my last VGA cable on the basis I wasn't going to need it. You know what they say, when you throw out a cable, as soon as you throw it away you need it. Well, actually no, I haven't needed it. So yeah, VGA I think is pretty much dead now, but you might still see it in installed legacy applications. VGA was replaced by DVI, which was an early digital technology. Again, I haven't seen DVI for years now. These days, HDMI is commonly used. HDMI is like a consumer level, which stands for high definition media interface. These days, you also see DisplayPort. So DisplayPort is an enhanced version of HDMI. The benefit for industrial application of the DisplayPort is that the DisplayPort technology includes latching on the connector. So with HDMI, you're under shock and vibration, the actual HDMI cable could fall out, but with DisplayPort, it can be latched so that you've got more protection against shock and vibration. And these days we also see Thunderbolt, which is a combination of DisplayPort over USB-C, and that means that we can use a smaller connector but still get all the benefits of DisplayPort and also have other communications going on with USB at the same time. So Thunderbolt is a very high performance network technology that can be used for displays, can be used for other interfaces. And with Thunderbolt and with USB-C, you can also get latching versions or screw connector versions of the USB-C connector as well, which prevents from falling out under shock or vibration. The displays themselves can use a variety of technology. The most common today is LCD, liquid crystal display, commonly with an LED backlight. It used to be in the early days of LCDs, we used a different sort of backlight which had a limited life, but with LEDs, they can last a lot longer. And also, if you're looking at consumer grade technology, you can have different zones of LEDs behind the screen, and that can improve the contrast, because what you can do is you can turn those LEDs off, so that can make that part of the screen darker. Otherwise, the way an LCD works is you've got different layers of liquid crystal, and what you'd have to do is turn all the liquid crystals on to block the light, so even black could actually have light behind it. But it depends on what you're looking for. If it's consumer technology and a variety of different ways of doing this, in more industrial PCs, then tends to be a bit simpler, but the LED backlight is very important to extend the life. You can also get organic LEDs or OLED. This is a sort of technology which again has better transistor technology, which can give you better blacks and so on. Also reduces the power consumption, but this tends to be more consumer and it tends to cost a bit more than just a standard LCD. These days we mostly see widescreen displays, the older 4:3 ratio that we used to get, like 1024 by 768. That's largely superseded by modern resolutions, 16:9 or 16:10. So something we used to see a lot in older cheaper laptops was 1366 by 768. Largely today that's superseded by high definition known as 1080p, which is a 1920 by 1080 resolution, very commonly seen today for 15-inch and above type displays. You can get Ultra HD, which is 3840 by 2160, also known as 4K. Not very common in industrial computers, but quite common on some laptops, particularly at the high end, and also for consumer grade TVs. 4K is pretty much standard. There's also Cinema 4K, which is a slightly extended resolution, 4096 by 2160. That gives you a slightly wider display, which can be used for some screens. Also, if you're editing graphics, it can help because you get an extra row of displays, an extra row of pixels where your controls can be. 8K is emerging for high-end TVs, but I don't see this as being that very common. It's effectively 4K monitors altogether, so an effective resolution of 7680 by 4320. But unless you've got a very, very large monitor, there's no point, because a 4K monitor is already at the limit of what a typical human can see unless you get very close to the screen. The other downside of 8K is the bandwidths are huge. It's effectively 4K monitors. That means you need 4 times the bandwidth, and for what? So maybe if you're into really, really high-end TV, 8K might be interesting to you, or these very high resolutions. But I think in practice, 4K is more than enough. And if you're talking about industrial PCs, then HD or 1080p is effectively enough as well. If you're smaller than 15-inch, then you may see smaller resolutions, and that will depend on the individual technology you're using. But even these smaller screens, the resolution is creeping up on those as well, because it helps from a programming point of view to have that higher resolution, because it means that then your display driver doesn't need to do as much work to convert to the different resolutions. And also, the actual technology we're using to create all of these screens, it just becomes cheaper and cheaper to make the same size of screen regardless of the application, and just shrink down the technology. So 1080p is certainly what you'd see for most industrial PC applications. And of course, that's where your widescreen resolution comes in. 1080p with 1920 by 1080, that's an effective resolution of 16:9. So yeah, that's what we commonly see today in terms of the actual displays themselves. Now I'm going to talk briefly about AI, or artificial intelligence. AI has its place in some applications, but we just need to be careful what we talk about with AI. That certainly with AI, there is artificial intelligence type algorithms, and there's a lot of marketing hype about those algorithms to call them AI, because AI is a bit of a buzzword, particularly right now at the time of generating this, because AI is being used in what's called large language modules, and those large language models, they are being used to emulate human speech, and very important for certain applications, maybe chatbots and a few other things. But AI encompasses a lot more than just that. And AI, as a sort of high-level technology, it can refer to specific algorithms which can be quite important in industrial applications. So regardless of the type of AI we're talking about, we are seeing CPU manufacturers adding AI cores to CPUs. So they call these NPUs, or neural processing units. So neural networks, this is a technology that's been around for a long time, and it can help certain algorithms. So particularly things where you're doing vision detection, then AI can be useful with those NPUs doing the neural processing. There might be some sort of pattern recognition that you might be doing. And again, that's a sort of algorithm which can effectively use that neural processing unit. We just need to be a bit careful about those different types of AI. And sometimes, vision recognition, I wouldn't really call that AI, but modern marketing means that people do want to call that AI. But it's really just an advanced algorithm that's detecting the edges of certain things and then building up a profile of the edge of whatever that is in order to then match it against predefined patterns. So is that AI? Well, it's sort of doing what the human brain is doing when we look at things. But to me, that's not true AI. Some people refer to AI as meaning a large language model like ChatGPT, but I would say those sorts of models aren't so useful in industrial applications. Probably what you'll see more likely in an industrial application is some sort of advanced algorithm that is quite compact, doesn't really match what an LLM can do, not even really intelligent, but does do very large amounts of calculations which would be quite difficult for a human to do. So for example, multivariate data analysis, this is something that you could use in an algorithm. You can detect various different aspects together, and then the idea is there with multivariate data analysis, you can determine what is the most important aspect of all your incoming data streams. So it's not really artificial intelligence, it's just a way of statistical number processing, but some people might refer to that as artificial intelligence. So with some of these CPUs, we are seeing AI cores in the CPU itself. Again, those AI cores are probably more focused on running LLMs rather than anything else. Another possibility is you can also have an external AI capability with a neural processing unit, or NPU. So this could be an add-in board. For example, there's a Halo NPU, which is available as an M.2 add-in. So you can add that to an industrial PC that's got an available M.2 slot. AI, of course, is both hardware and software. You need the CPU or the GPU or the NPU to process the artificial intelligence algorithm, but you might also need an AI framework in software. So for example, TensorFlow, Keras, PyTorch, Onyx, or of course, if you are doing work with LLMs, then you would use whatever your preferred LLM is, and you can download these models and run them locally. And that's where your software framework comes in, along with the underlying hardware that's actually going to run the AI core. So it's quite interesting in terms of how that's growing. Definitely there are applications for industry, but when we talk about ChatGPT and similar large language models, that's not really what we mean by AI for industrial applications. We would be talking about advanced algorithms instead. Let's take a look at the interfaces that we might use for industrial PCs. Interfaces are required to link to external equipment. At the physical layer, that can include Ethernet, USB, serial. There might be legacy connections for keyboard and mice, although often today these are USB. In industrial applications, you might have field buses, for example, Profibus, DeviceNet and others. There are also internal interfaces for peripherals inside the industrial PC, and some of these might also be exposed externally. So we talked about serial ATA for hard disks, PCIe, which is an internal high-speed bus for graphics, M.2, which is a sort of electrical connection specification that can also include PCIe as the actual specification for communications. So there are multiple interfaces that may or may not be required depending on what your application is and what you're actually trying to connect to. Now, the downside of these interfaces is every time you have an extra interface, it adds costs because you've got the cost of the silicon, the chip, to do the work, and you also need a connector, and then potentially you also need work in the software as well. So there'll be an interface at the BIOS level, and then there will also be a driver at the operating system level. Having said that, we normally need a certain number of interfaces, and it doesn't add that much cost because we need them regardless. So commonly in an industrial PC, you'll find USB connections, which can have multiple uses, and it doesn't really add too much cost to add or have a few more extra USBs than you might need. Ethernet, again, the cost of adding a Ethernet connector along with a switch, it might be internal to the industrial PC, so it needs some real estate on the board, but the actual amount of electronics and the amount of connector technology, it's minimal. If you really wanted to save every cent or every penny, then you might be concerned with minimizing the number of interfaces. But in the overall cost of ownership of the equipment and the overall cost of the industrial PC, the savings that can be made by trying to minimize the amount of connections you have, it's probably not worthwhile. So what you might find is, some vendors with their industrial PCs will let you configure everything down to exactly the level you want. But of course, if an interface is missing, it can't easily be added afterwards, because if the chip is missing or the connector's not there, that might be difficult. You can always add it via a PCIe card, of course, if you've got a PCIe connection. But the other side is, if you have more than you need, then it's not really costing that much. Yes, it's slightly more space, it's slightly more silicon, but for the vendor, it might be that it's cheaper for them to make multiple units of the same type rather than allow vast customization opportunities, which can allow the user to save just a few cents. So again, depends on the market, depends on the user, depends on the vendor. But I would say generally it's better to have more interfaces when you need and not use them, rather than trying to cut the system down to have the exact number you need. It can also be spare holdings as well. If you've got multiple applications, you might have some applications which need 2 USB ports, some which need 4. If you've got one device with 4 USB ports, then you can have one spare that can cover both use cases. So it might be cheaper to reduce your spares holding and have more than you need on the basis that will cover all your installed base. So quite a lot of interfaces, quite a lot of implications, but generally it's not too much adding in terms of costs and price and performance. So easier to have more than you need rather than less. We mentioned heatsinks earlier. Let's talk about how heatsinks and enclosures are linked, and also to talk about the sorts of enclosures that you might have. So in the commercial PC, you usually have a motherboard, and that has sockets, and there would be a heatsink and a fan to cool the components. And if you're building your own system, you can purchase those separately. So you buy your motherboard, you buy your CPU, you plug those in, you mount the heatsink on top of that motherboard, and you install that in a case, and then you would have a variety of fans. So there might be a fan on the heatsink, and there might be fans on the enclosure as well. And if you're really into cooling, you might have multiple fans. You might even be looking at liquid cooling, and you would take that decision based on how much noise you can cope with, because fans can be noisy. The reliability, of course, because fans can be unreliable. Typical MTBF on the commercial fan is only 3 years. So if you're using your system regularly, you might need to replace fans. And also cost, of course. The more fans you've got, the more it costs. And size. Fans do take up space. And you've got to do something with the air once the air comes out of the enclosure. With commercial PCs, normally you've got plenty of space. It's mounting on a desk or under a desk. Maybe it's in a server enclosure where you've got a few more constraints. But you're not too much concerned with the enclosure and the heat sinks and getting rid of the heat. You would use the appropriate technologies there. With an IPC, these are typically much more ruggedized. So you'd have a ruggedized motherboard, often a passive heatsink, so there's no fans. And in many IPCs I've seen recently, the technology is designed so that the enclosure also acts as the heatsink. So what you typically have is a steel, or more likely an aluminium enclosure. The aluminium enclosure is tightly bolted to the motherboard, along with heat spreader and other technologies which get the heat from the chips and put it out into the enclosure. And then the enclosure would have vanes on, and what you're relying on is ambient airflow to take the heat away by flowing over the vanes of the actual enclosure itself. So far we've focused on the hardware of the industrial PC. Let's talk briefly about the BIOS, the operating systems and application languages that you might use. So all computers have what's called the BIOS, or Basic I/O System. What the BIOS does is it provides services to the operating system to interface with the actual hardware. And these days, we also need to consider cybersecurity. So we need to have a secure interface from the operating system to the hardware. Now, the reason we have the BIOS is in the olden days, there were multiple different types of I/O, and we would communicate with those in a wide variety of different ways. So the BIOS was a way of standardizing that interface to be able to have a simpler interface into the operating system itself. These days, we've got more memory capabilities, we've got better software. So the BIOS now can be a bit more basic in terms of what it provides. But either way, you do need this interface to the operating system so the operating system can communicate with the hardware in a sort of standardized way, rather than having to have an individual driver for every single piece of hardware that's out there. That also affects the operating system as well, but we'll come on to that. Now, the BIOS itself, normally it's contained on the motherboard. So that would either be in battery-backed RAM. So you would have a battery, typically a coin cell battery, that lasts anywhere from 5 to 10 years. If that battery goes flat, then of course, if you power cycle the motherboard, you would lose the BIOS. So normally what the BIOS would do is there would be some sensible defaults which would at least allow it to boot. More likely in modern systems, you'll see the BIOS is, previously it might have been in electrically erasable programmable read-only memory, or EEPROM. More likely these days it's in flash memory, so it will survive across a power fail, and that minimizes the requirement for batteries. So what the BIOS does is when the computer starts up, it performs a power on self-test, and then it allows configuration of the hardware at boot time. And that can include enabling and disabling devices and features. So for example, we mentioned previously, you might have 4 USB ports, but from a cybersecurity point of view, you might want to disable unused USB ports. So that could be configured inside the BIOS itself. So the BIOS configures the hardware after performing the self-test. There might also be some cybersecurity interaction in there, often combined with things like a trusted platform module. You might be doing things like timed boot and secure boot to make sure the operating system and everything else is trusted. So all of this is part of your startup process. And then what the BIOS does is it hands off to the operating system, and then the operating system is loaded and powers up. The BIOS is still there, of course, because the operating system might be communicating to the hardware through the OS, based on what the configuration and the power on was performing. Now, BIOS these days, we often use what we call the Unified Extensible Firmware Interface, or UEFI. That's used for these boot and runtime functions. And the key point of the UEFI is, that provides enhanced cybersecurity with some of that capabilities like secure boot that I mentioned. So not every device will have that, but increasingly, we are using that UEFI. And then that UEFI can also include graphics capability as well. So that means you can have a more attractive BIOS. So you see this in modern motherboards. When you boot up just using the BIOS, you actually get a graphical user interface, not just a very simple text-based interface that older BIOSes would give you. But that's just a presentation thing. The actual functionality of the BIOS underneath that is the same. It's just the way it presents to you when it loads. So once the BIOS has completed its self-test configuration and enabled or disabled devices, it then loads the operating system. Typically, the operating system involves loading lots of processes from a hard disk or an SSD into RAM, and then the operating system is the actual software that runs the computer. So effectively, it provides services which interface the hardware to your application level. So the BIOS is still there at the bottom layer. You've got the operating system on top, and then above that you'd have your individual applications you use, such as HMI SCADA, or maybe you're using your Office type applications like Word or Excel or so on. Those are all running at the application level, but they need to sit on top of the operating system. The operating system can be a nice graphical user interface, or it could just be a command line based operating system, and depending on which you use will depend on what your requirements are and what you need to run. So what we often see is Windows 10 or 11, they're the commonest desktop operating system. They are biased towards desktop use, and they give you a graphical user interface with both a high quality display and an interface with keyboard and particularly the mouse for interacting with the system. For server applications, we see Windows Server. Windows Server is based on the same underlying code to some extent as Windows 10 and 11, but it's more biased towards user management and file management, and maybe running a SQL or an SQL database such as SQL Server. So there may be a graphical user interface, but in some servers there isn't. It's just running in a blind mode. Maybe there's a very limited GUI, or maybe there's nothing there. But the idea is we now focus more on the computer running as a hardware resource rather than more of a graphical resource with a graphical user interface. Now there is a version of Windows 10 for embedded devices. There's various different versions of this. There's Windows 10 IoT Enterprise, which is the same as full-blown Windows 10. There's also Windows 10 IoT, which is a very much cut down version, which can also run on non-Intel CPUs or non-x86 and x64 CPUs. So the key difference is, there's two different operating systems there. Windows 10 IoT Enterprise is the same as Windows 10, but with a different license model, and it has the bloatware turned off. It doesn't necessarily have to connect to Windows Update. And also what you find with these typical Windows 10 IoT Enterprise editions is they use a long-term servicing channel, and that gives us support for up to 2032, as well as control over updates. One of the main reasons you often see Windows 10 IoT Enterprise versus Windows 11, and there is an IoT version of Windows 11, but the big difference is Windows 11 really needs you to have a Microsoft account, which you might not want with an embedded application. And also Windows 11 likes to connect to the internet, which is also something that you might not want to do with an embedded application. So these days, Windows 10 IoT, although Windows 10 is coming to the end of its life in October 2025, Windows 10 IoT Enterprise with a long-term service channel still has a long life ahead. And the Windows 10 IoT for embedded devices, that's a cut down version, again, a different license model, and it's even more restricted, and it can also run on alternative CPUs like ARM chips. So that's similar capabilities and look and feel as Windows 10, but again, designed for embedded applications. And with the Windows 10 IoT, you can actually, as a vendor, you can choose which services you install and configure. So it gives a vendor of, say, an operator interface a lot more control over what they install. Now, Linux is becoming popular for embedded applications. It's open. There are free versions. It's very lightweight. The thing about Linux is you can build a Linux version which can be very, very small. Windows 10 or 11 typically take up at least 20 gigabytes of hard disks, whereas Linux can fit in as little as 1 gigabyte or even less. Same with memory. Windows 10 can run in 4 gigabytes of RAM, but it's very tight. Windows 11 I think needs 8 gigabytes of RAM or more. So it needs quite a lot of system resources, whereas Linux, Particularly if you're using the one without the graphical user interface, Linux could easily run in 1 or 2 gigabytes of RAM, and with a graphical user interface, it's very powerful in 4 gigabytes of RAM. So Linux is very popular, and the great thing about Linux being open, there are lots of things you can run on top of Linux because it's widely used for server and embedded applications, including all the way up to things like HMI SCADA, maybe using a web server, lots of language support, which I'll come on to. So Linux is becoming very common in embedded applications. For real-time control, Linux is sort of real-time, but not quite. Windows 10 has real-time extensions, but it's not really real-time. So if you want the true real-time embedded operating system, you could use something like QNX or VxWorks. And those are for applications that require very strict deterministic control with very good support in the operating system and the application level to stop applications running away. So for example, they've maybe got better memory protection, they've got things like watchdogs to prevent routines from running too long, and there may also be specific ways of handling interrupts to make sure that things can happen in a true deterministic manner within a predetermined amount of time. Whereas you might not get that with Linux or Windows 10. They might execute an interrupt, but there might be some delay before the interrupt actually happens, and that delay might be variable depending on what else the computer's doing. So if you want a true real-time application, you'll probably be using one of these real-time operating systems. Now, you may be using your industrial PC with a predefined application, such as a control programming application development environment or HMI SCADA environment, but you may also be developing an application yourself using a common programming language. These are the top application languages which people use to develop applications. Java is number one. It's used for Android applications, and also a derivative of Java is JavaScript, which is used inside web applications. Python is an upcoming language which is possibly approaching and maybe even overtaking Java. Python has the benefit of being much easier to learn. It looks better. There's a wide variety of libraries as well for Python, which means it's very easy to do things which are hard, because you can just go out and find a library which does that function for you, and that's already implemented. Now we've also got traditional languages like C, C++. These are very fast and efficient, but they're harder to develop applications in. But interestingly, if you're using Python, you're effectively already using C, C++, because a lot of the libraries are written in C++ themselves as well. So yeah, Python, some people say it's easy to learn, and it is, but you're also leveraging older underlying technologies which give you that speed and efficiency. JavaScript I mentioned, a lot of web pages run JavaScript. C# is a sort of Microsoft version of Java. PHP, this is a server-side programming which is again often used in websites. Objective-C, this is used for iOS apps running on iPhones and iPads. It's effectively Apple's version of C, not really very important in industrial PC applications. You've got SQL or structured query language. This is used for database queries, so these are often embedded inside one of these other languages. And then also very common in HMI SCADA is BASIC. BASIC, this is the beginner's all symbolic instruction set computing language. It's embedded inside VB.NET. So VB is Visual Basic. VB.NET is a .NET version of Visual Basic. It's old now, and it's maybe completely surpassed by these other languages, but it's very common in HMI SCADA because it's been the standard for about the last 20 plus years. We also see VBA, which is Visual Basic for Applications. This is another version of Visual Basic that maybe again superseded today, but still widely used because it's been around for a long time. And VBA was the underlying programming language for things like Excel, Word, Access, and so on. So if ever you wanted to do any sort of automation inside those applications, you'd be writing in VBA. So we've touched on some of the applications that industrial PCs may have. There are multiple options for use in industrial applications. Typically, we could run an IPC as an embedded controller. That might be using a real-time operating system like VxWorks, And that would give us a true real-time capability to perform our real-time control. So we might be controlling something like a gas turbine at the high end. We might be controlling as simple as something like a simple conveyor at the low end. But those embedded controllers, they often run one of these real-time operating systems, and then on top of that would be some sort of real-time application development language, or maybe you would be running one of those languages we just talked about recently. But common languages, there would be the PLC vendors who have their own programming capabilities, and then there are more open programming applications like code assist and so on, which let you run IEC 61131 Part 3 languages on top of an embedded controller. Another common application is for edge data collection and analytics. So the edge refers to the edge of the network. So from an IT-centric point of view, you've got your servers, and as you move further away from those servers, then you get towards the edge. So the edge is effectively where your network ends. So that could be at the machine level, it could be your process. And then if you've got distributed environments, for example, if you're a water company, those edge devices might include pumping stations or other plants which are a long way away from the central IT department. So we often want to get data from those edge applications. So we could use an industrial PC as a data collector. And we might also want to be running high-level analytics. So for example, in a water or wastewater application, we might want to be optimizing the usage of the pumps based on what energy prices are. So when energy is cheap, we might want to turn those pumps up to speed up the processes. When energy is expensive, we might want to turn those pumps down and save energy. We might also use HMI SCADA. HMI SCADA, that's human machine interface or supervisory control and data acquisition. So often we have an embedded PC, an industrial PC to run as the server, and then that serves up the screens to remote clients, which might be displays. So HMI SCADA, server and client, and sometimes they can be combined on the same computer. Now, I often see IPCs being used for other interfaces as well. Industrial data storage is one example. So either data collection and remote storage, or data collection and local storage. Communications gateway between different devices. There are many different devices with different protocols out there. So a good example of using an IPC is as a gateway between those different protocols and devices. For example, Profibus to Modbus TCP, or you might have serial to Ethernet and so on. Some of those have particular embedded applications or almost like appliance type applications, but with the low cost of some IPCs, you might use an industrial PC for that purpose. Operator interfaces, that's a class of an industrial PC, typically with a low cost embedded CPU and a low cost embedded operating system. And then you get up to the full-blown Windows again. So HMI SCADA server, HMI SCADA client. The client would have the display, and they may well be running on Windows 10. And then we also get thin clients. So we might be talking about something that's based on a web browser or using remote desktop protocol or terminal services. So that's an example of where we want to display data for the operator at the machine, and that's where we might use some class of industrial PC. It's worth touching on hypervisors and virtualization. What we find with modern, very powerful computers is they're almost too powerful. A lot of the time, they're just sitting there doing nothing, waiting for the next request from the application or from the user. So what we can do is, and also by leveraging multi-core technology, we can potentially run hypervisor software to split the CPU into multiple virtual machines. So the idea now is we can run multiple operating systems on each individual virtual machine. Each virtual machine has its own storage space, its own allocated memory, its own allocated peripheral access, and by separating the systems in this way, it allows us to use a more powerful computer for multiple purposes instead of just one. And it also improves applications in terms of their performance, because we can allocate their own requirements according to what they need. And also it improves things like cybersecurity as well, because the individual computers can be separated from each other. Hypervisors and virtualization, this is very much favored inside the IT world, because it means they can reduce their hardware count while still allowing them to manage their applications as individual computers. So very good for splitting up your multiple applications, but still only having fewer numbers of computers. There's a slight downside, of course. It means if your computer fails, you lose everything. So often what you'll find is in the larger virtual machine space, these computers might be fault tolerant, or they might be networked in such a way using clustering or other technologies, so that if a virtual machine on one computer fails, then the corresponding virtual machine on another computer can take over. But that's very much at the high level in the IT world. At an industrial level, the great use of hypervisors and virtualization is to allow a single device to run multiple applications without interface, without interference. So for example, you might have an industrial controller which runs your high-speed VxWorks real-time operating system, and you could also run a HMI SCADA using a different operating system such as Linux or even Windows, all on the same computer. So the benefit is a single box, so reduced panel space, reduced wiring, single power connection. Often you could have a virtual Ethernet connection between the devices as well, so that reduces your external wiring requirements. So it's an interesting option. The only thing you've got to be careful of is how much extra is your hypervisor costing you, and also what happens if your single box fails. But again, you've still got a high degree of isolation between the virtual machines. If one machine is powered down because maybe you need to power cycle it to install updates, the other virtual machine can carry on operating without any interruption. It's only really if your underlying hardware or your underlying hypervisor actually causes problems. Now there's two types of hypervisor. There's type 1, which runs at a very low level, just over the top of the BIOS, so you don't need an operating system. And then we also have type 2. A type 2 hypervisor runs on top of an operating system. So you'd have Windows, for example, with the Microsoft virtual machine technology, and then on top of that you'd run multiple virtual machines. Or you might be running ESX. ESX is a type 1 technology where ESX effectively is your operating system. It performs very minimal operating system functionality, but it does allow you to run all of your virtual machines on top of that ESX instance. So different types of interface, different types of the actual virtual machines itself. And there's a variety of vendors available. Microsoft, they have their own technology. Oracle have options. VMware is another common one. And then there are also some industrialized type virtualization operators out there as well. So a great thing about hypervising and virtualization, reduces the amount of computers you need and takes advantage of the high performance that we can get with modern computers. But there is a potential risk in terms of putting everything in a single server. So you might need to still look at some sort of redundancy at the computer level. Now, containerization is a similar concept to virtualization. Often what we find is one of the big benefits of virtual machines is being able to have individual computers which are separated from each other, and that means it's very easy to replace software at a virtual machine level, and also because they're isolated we get good cybersecurity protection between them. The downside is though that with virtualization you need multiple operating systems because each virtual machine has its own operating system to perform the basic functions. So with containerization, it's a similar concept to virtualization. Each container has its own storage space, its own memory, its peripheral interface. But the difference now is they share the same underlying operating system. So this allows a single device to run multiple applications without interference as before, such as an industrial controller and HMI SCADA, but they would have to run on the same operating system. So similar benefits to before, reducing the hardware costs and the panel space, etc., allows us to swap out containers quite easily. But the big benefit is it uses fewer system resources than virtualization. And of course, that could potentially save costs as well because you don't need as many operating system licenses. So we're seeing containerization as a very popular concept, particularly in smaller computers compared to a virtual machine. Allows us to run lower levels of hardware, smaller amounts of memory, smaller amounts of disk space. And one of the major container vendors is Portainer, which allows you to run these particular containers, and Docker is another one. So a variety of different options there for simplifying your hardware arrangements, but without the extra cost of multiple operating systems. Now, a concept we've sort of alluded to so far, but haven't really mentioned as such, is the ideas of layering. Layering inside a computer is quite common. You'll see that there's the layer of the CPU itself. Underneath the CPU, you might have the individual interfaces to the devices. Above the CPU, you have the operating system, and between the operating system and the CPU, you have the BIOS. So straight away, we've already got 4 layers there. And if you add on the application, that gives us a 5th layer. There's also layering at the Ethernet layer as well. There's the ISO Open Systems International ISO model, the 7-layer model as it's called. So we get something similar with the hardware. Now what we can do is we can have additional layers at the hardware, and this is where ComExpress comes in. ComExpress isn't as popular as it used to be, but it used to be quite common in industrial PCs because it gave us an additional layer to isolate the hardware layers from each other. So starting at the bottom, as I say, you've got the I/O itself, then you've got the CPU, then on top of that you've got the BIOS, on top of that you've got the applications and the operating system. So what ComExpress is, it gives us an extra layer of the hardware which potentially gives us a bit more flexibility. So the idea of ComExpress is computer on module. So it effectively splits your CPU layer. So rather than have one motherboard with the CPU on it, what you now have is you have a motherboard, and on top of that motherboard you have your computer on module board, and the computer on module board contains the CPU, the chipset and the memory on a very much standardized daughterboard. So what it potentially means is you could have a carrier board or your motherboard which could stay the same for many years, but you could upgrade your computer on module board, your ComExpress board, and that could be upgraded more easily. Some vendors also use ComExpress as a way of standardizing their designs, so you could have a simple set of ComExpress boards but with multiple different carrier boards. So for example, you might say I'll have a custom enclosure to create a display, I'll have a VME interface. VME is an old interface. You might have a PCI interface. You might have an industrial PC. So what you could do is you could use that same ComExpress board across multiple different hardware devices without having to keep redesigning your CPU boards. Now this made a lot of sense when industrial PCs and devices were a bit more expensive. The ComExpress board itself could be very compact. It was about the size of 2 credit cards, depending which size of ComExpress you went for. And what it potentially means that if a processor ever needed to be updated, you could replace the ComExpress board or update the ComExpress board without having to update the underlying hardware. There's a downside though. It's first of all it is a standard, so there's potential licensing fees to the standardization authority. It does now require 2 PCBs, so you've got extra weight and complexity. It also requires connectors, so there's extra weight and complexity there. And I think what a lot of people found was, yeah, ComExpress does give you some flexibility, but ultimately a monolithic design, certainly if you're talking about higher volume designs, a monolithic design allows you to have a more effective design with fewer components. There would just be one PCB, there would just be all of the chips on the single board. Certainly as we move towards more system on chip type applications now, the whole idea of having a ComExpress board is going away to some extent. Now, a big factor about industrial PCs is performance. We've covered a lot of performance aspects because we talked about performance at the hardware levels. So of course you can always improve performance by having more cores. Each individual core can be faster. You can have more cache. There might be improvements you can make at other areas. For example, you might have faster interfaces. And there's a lot of things you can do there to improve the performance of industrial PC. But one of the biggest things you can do is eliminate bottlenecks and improve performance at the application layer. But let's explore some of these areas where we can make improvements and how we can eliminate bottlenecks. So my view is that application optimization, this is the number one thing that affects performance. Now we see this, people often prototype an application. They will just write the software in a way that's as simple as possible in order to get it working. Often also referred to as maybe the minimum viable product. Maybe it's just that the developer is focused on getting a quick result. And what that often means is they choose default algorithms which may not be the most efficient for the actual application you're trying to resolve. But the good news is, of course, is you've got a working application, you've got something you can ship, something you can use. So often that's good because you're where you need to be, and then it might be that that's as far as you need to go. But what you might find is when you combine that application with other applications, it now is affected by other things going on. Maybe there are other bottlenecks in the system, maybe you're running it on different hardware. So as I mentioned, yeah, there are lots of things you can do, but my view is that the number one is normally optimizing the application itself. So I mentioned, of course, yeah, we can improve the clock speed, so we can run the application faster. We can improve the number of cores, but that might not help with the application if the application only runs on a single core. We can improve the number of threads, but again, that won't help if the application isn't optimized for more threads. Cache memory can help, but again, some applications, if they're using main memory, it won't help that we've got bigger cache memory because they still need to go out to the outside world. Pipelining capability, that can help, because even in a single core, single threaded application, pipelining can help us with some of our applications. Of course, we can look at main memory type and speed. We can check the hard disk type and speed. SSDs are often significantly faster, and certainly for many applications, changing hard disk to SSD makes a big difference. Of course, network interfacing and I/O speed can make a difference, and so can your graphics card interface and the GPU speed and the GPU memory. But ultimately, it often comes down to how fast is your application. And there are multiple algorithms you can use which can help, and depending on what your algorithm is and what the application is, changing your algorithm, particularly for things like searching and sorting and for other applications, changing that application can significantly improve your application speed based on improving the efficiency of those algorithms. Now, generally what we do is, to remove bottlenecks, to improve performance, it's an iterative process. So we would go around and look at each process in turn and then try and eliminate what that is, and then you'd have an additional bottleneck in future. So for example, it may be, I've come across older systems where the computer was constrained by the network interface. In the olden days we used to use like 10 megabit internet, or Ethernet rather. So with a 10 megabit Ethernet interface, you're constrained very much by what that Ethernet can support. You could get significant improvements by changing to 100 megabit Ethernet. Once you've changed to 100 megabit Ethernet, now you'll find that something else is slowing you down. So maybe it's your memory interface. So maybe you would go from single channel RAM to dual channel RAM, and that would eliminate that bottleneck. And then you get to the next bottleneck. So maybe the next bottleneck after this is your CPU is too slow. So you may want to increase your CPU speed. Now, the reason it's an iterative process is you have to remove the bottlenecks in the right order. If you remove them in the wrong order, you don't improve performance. So if your network is the limiting factor, but you upgrade your CPU, that doesn't help. Your CPU is processing faster, but because now you're constrained by what your network interface can do, it just means that your CPU will just be spending more idle clock cycles waiting for data to be sent or received over the network interface, and it won't actually improve your performance at all. So there's a variety of tools you can use to investigate what your bottlenecks might be, and then the best approach is eliminate each bottleneck in turn before moving to the next one. Otherwise you can waste a lot of time and money improving something, but you're still constrained by the other underlying bottleneck. So as I said, my number one issue with most embedded applications is that they are not optimized. And that's challenging. There are lots of programming skills which may not be accessible by the developer of the application. So it's all very well to choose, say, a simple search algorithm, and that might be efficient. It might be something that's worked in the past, but it could be this application is different, and it may be a different search algorithm will be more suitable for the application. But working out which algorithm to use, that can take time and money. You might have to do a lot of investigation. And of course, depending on who's doing the development, especially for advanced algorithms, it may be beyond the skill of the developer to be able to understand which algorithm is going to be the most suitable. Still, it's the most important one, I think. Improving the suitability of the embedded application by optimizing the algorithm is probably the number one way to work. Now, what you can then do is, you can use performance counters to find the initial bottleneck. Typically what you do is, and with Windows, you've got various performance counters you can use. What you do is you'd look at those counters to find out where your performance is. And what you're trying to do is find the one that's at 100%. If you find one that's at 100% while others are lower, then that indicates that that one counter that's 100% is a bottleneck. So again, using that previous application experience, you could look at the Windows performance counters. You can do this in the Task Manager. So in the Task Manager, you might see your network is running at 100% and your CPU is only running at 20% and your graphics are running at 10% and maybe your memory interface is running at 12% or whatever the numbers are. We can easily see from that comparison that we've got 100% bottleneck in the actual network interface itself. So that would either mean we would optimize reading and writing over the network, or we might go to a faster network technology. Maybe, as I said, in the olden days, you go from 10 to 100. These days, we might go from 100 to a gigabit. And then we would see that that network counter goes down. And then we might find that another counter goes up. So maybe the graphics is constrained, or maybe the CPU is constrained, or maybe the memory is constrained. So what you can do is, you can look at that bottleneck, find out the counter that's 100%, improve that counter, and then repeat those tests iteratively to find the next bottleneck. There may be a limit to the improvements you can make. There may be economic constraints, there may be technical constraints. It may be that in an old computer, there's not much you can do. If you're limited to 100 megabit connections, it's very difficult to improve that to a gigabit. So you may be stuck unless you're willing to spend money to completely replace that industrial PC. But there may be other things you can do. Maybe you could look at what else is on the network, and you might be able to segregate the network. You might be able to improve the backbone of the network. For example, you might be able to replace a network switch from a 100 megabit version to a gigabit version, and that could help overall, because although you're still constrained by 100 megabit at the industrial PC, the actual switch itself can handle more data. So there are things we can do, but ultimately you may hit a constraint where only limited improvements can be made. So I would say number one is the application itself. Certainly look at the network, because that's often worth looking at. Then you come to CPU performance, and then after that it's often RAM. But these days, RAM is often difficult to upgrade, particularly if it's soldered onto the board. So you might be looking at making an improvement by replacing the industrial PC entirely. And then it might be worth doing that. If your industrial PC is already 5 years old, you might by now be running an old, outdated operating system, which is insecure. You might be running an old version of the application, if it's say HMI SCADA or whatever. So maybe at 5 years' time, you've got your return on investment. It's now worth looking at that bigger investment in order to do a more comprehensive upgrade of the application to make it more faster and more reliable. And often that also comes with additional improvements as well, like cybersecurity improvements. So let's summarize what we've covered. The key point is that embedded computing and industrial PCs are very similar in concept to commercial computers, but there's extra emphasis on certain aspects that are important to industrial applications. The key one is probably ruggedness. A typical industrial PC would have no moving parts, so no rotating hard disks, it would all be SSDs. No fans, because fans have a limited life. They would have a higher level of operating temperature. So whereas a commercial computer might be 0 to 40, a typical industrial PC is more like 0 to 60, and maybe even bigger than that. Minus 20, minus 40 even, maybe all the way up to plus 70, maybe even plus 85 in some applications. Shock and vibration are important. You often get constant low-level vibration on industrial applications, and you might get high levels of shock, which don't occur as often, but that shock and vibration might damage a commercial grade computer, but an industrial PC needs to be able to cope with those. Now you also need to consider long-term manufacture and supply with the same configuration. You're really looking for a vendor who will offer you the same configuration for up to 5 years with no changes, possibly even longer, but 5 years would be good, because that would allow you to run out with the current operating system cycle and also probably the current application cycle before you need to consider major upgrades. Now 5 years doesn't sound like long, but a lot of commercial PCs don't last 5 years. Or if they do, after 5 years, they may be getting very much towards the end of their life and need replacement. And it may be they don't support the operating system upgrades and so on you need. 5 years in an industrial application, however, is quite short. And while we don't have the same pressures around the operating system and the applications, you still need to consider that maybe 5 years is what you would need before replacement, although you may be aiming for up to 10 years or more. But the key point there is about the same configuration. If you buy a commercial computer 1 year, it can completely change for next year. Intel CPU cycles we mentioned are about 1 to 2 years. The support chips may even change on a day-to-day basis. I've had this in the past where I've bought Dell computers, and you buy a Dell model 1 week, the following week you buy the same underlying Dell part number, but it arrives with a slightly different configuration. It might be minimal, it might be the network chip has changed, or it might be the sound card has changed, or it might be some change to some other thing that's minor from a commercial point of view because the commercial user doesn't care. But from an industrial point of view, if you've qualified your software stack to run on a particular set of hardware, if that underlying hardware changes, you need to requalify your hardware stack. So that might involve some testing. Maybe it's only a week of testing, but a week of testing, that can be a lot of time if you've got a limited number of developers. And then, of course, it means now you've got multiple versions out on the site or out on your plants. You've now got to update and maintain multiple versions. So, generally, it's much easier if you can have a single configuration which doesn't change at all from any one version to another version. Now, you may also be looking for customization to meet your application requirements. I would say don't worry too much about saving costs. If you're just concerned with, say, removing an interface to save a little bit of money, you might want to do that for cybersecurity reasons, but you can often turn that interface off in the BIOS. More likely, people want to have customization to reduce costs, but over the long life of these products, that can be counterproductive because application requirements may grow. So you may be better off with, say, a bit more RAM now because, yes, it costs a bit more, but over the life of the product, as you upgrade the operating system, as you add more application capabilities, you may need that more RAM in future. So better to have RAM you don't use today and might use in future rather than have to scrap and replace the whole industrial PC in future. But customization can be important, and it might be there are particular things you need which you can't get from normal vendor, and there might be an industrial vendor that can offer that customization. Legacy interfaces, this can be important. Your industrial PC might be quite new and the application overall might be quite new, but you may well need to integrate with legacy applications using old interfaces. For example, Profibus or DeviceNet, or even serial interfaces. RS-232 and RS-485 are not common. In fact, I don't think I've seen a commercial computer with an RS-232 or 48 interface for a long time now. So even simple legacy interfaces, industrial PCs can continue to offer those, whereas you might not get that from your commercial supplier. And you need performance to match price. Of course, embedded computing, you may get slightly lower performance than an equivalent commercial one at a higher price. So you've got to think about the long-term cost of ownership, and you've got to think about your current and future requirements. But ultimately, you want to spend the amount of money that you need to match your performance that you require. So particularly, for example, with an embedded gateway, if you're only transferring a few values, you don't need a very high-powered computer to do that. So it's helpful if you have a look at various embedded computing devices which have the required level of performance at a relatively low price, so you're not over-specifying what you do. And that extends beyond just the performance of the device. That also extends to power consumption. It includes the things like heat dissipation, and even other aspects like how does it mount onto the panel? Is it DIN rail mounting? Is it panel mounting? Do I need any special connectors? So there's a lot of aspects there, and that's where embedded computing, you need to take a bit more attention, because you're not just using standard commercial interfaces like USB and HDMI. You might need different levels of interfaces there. So embedded computing, it is based on standard commercial computers, but there are quite a few different things to consider there about cost of ownership, the hardware that you implement, are you using the latest CPUs and so on. And hopefully I've covered all of these aspects, and now you'll have a better understanding of how an embedded computer can meet your requirements.